Where did the universe begin? It is a question that lands like a stone in still water, sending concentric ripples through every field of human thought. It is at once simple and insoluble. Did everything, space, time, light, the laws that bind matter, and the beings that ask the question, emerge from a single instant? The thought presses against the ribs of reason and the soft tissue of imagination, and it leaves a hollow no answer can quite fill. The question arrives not as a theorem, but as a sensation. It sits in the chest like cold glass. The mind tightens around it, trying to frame it in language that will not crack under the weight of paradox. To imagine all that is collapsing into one origin is to imagine every horizon removed, every preface burned away, the entire ledger of causality folded into a single line. The shock is visceral, even in its phrasing. Where did the universe begin? There is an accusation, as if the cosmos had committed an unspeakable theft and left humanity to inventory the loss. There is fear in that vacuum. There is exhilaration. There is a peculiar humility, an awareness that the scale of origin dwarfs the most expansive human emotions. When the human mind confronts such enormities, it experiences the same oscillation found in the first moments after any profound revelation: denial, curiosity, a numbing awe that clears the immediate mind and allows larger questions to step forward. The question itself becomes a lens, and through it the world seems newly fragile and spectacular. To propose that all existence radiated from one point is to rewrite the map of reality. The idea is at once geometrical and metaphysical. If space and time themselves were not always there, if they unfurled in a primordial event, then causation loses its accustomed footing. There is no before in ordinary terms, because before presupposes time. The human language, accustomed to linear sequences and family trees of cause and effect, stumbles. A single moment origin asks the listener to unmoor temporal intuition, to feel what it is to stand on the shore of time and imagine waves beginning not at the horizon but beneath the sand. The emotional landscape that follows this mental exercise is rugged. A person might register it as vertigo, a deepening silence at the back of the mind that will not be filled with the usual chatter. Later, when the mind reasserts itself with narratives, myths, equations, metaphors, it clutches at images bright enough to keep the darkness at bay. Myths picture births and floods and primeval fires. Modern science renders the opening in numbers and graphs and background hums. Both modes are human attempts to translate the ineffable into something that can be held and shared. Their difference lies in method, not in the trembling insistence beneath, a need for explanation, reassurance, orientation. Humanity's attempts to answer through art, ritual, and calculation are themselves a record of that trembling. For millennia, stories rose like scaffolding around the question of origins. The earliest tales spoke in gestures, a world hatched from an egg, a god who spoke and unrolled the sky like parchment, a dreaming animal whose exhale pulled apart stone and sea. Each story was less about facts than about the human relationship to ungroundedness. How to live knowing the furniture of existence might have been scattered by a capricious hand. Those narratives promised coherence, a place to set the small domestic affairs of living, naming the stars, measuring seasons, binding social order to cosmic propriety. The modern narrative is different in texture, but not in aim. Scientific cosmology seeks a map and a mechanism. It infers a beginning from whispers, radiation that bathes the universe, the redshift of distant galaxies, the distribution of elements, small, reliable clues that read like fingerprints on a blurred photograph. The language here is deliberately restrained, probabilities, margins of error, models that are always provisional. Yet beneath the measured tone, the impulse is the same as the myth-makers. There is a yearning to lift the veil, to place origin into a comprehensible framework. That yearning is also an intimacy with deep time, a scale for which human intuitions are ungainly. To make that scale sensible, the imagination must do more than count in billions. It must invent metaphors that compress the human lifetime into a meaningful fraction of the cosmic calendar. In one such compression, the entire 13.8 billion year history of the universe shrinks into a single year. In this calendar, the first atoms appear in January, galaxies assemble through spring, the sun and earth take shape in late September, and complex life blooms in November. Modern humans do not appear until the last hour of December 31. The entire span of recorded human history fits inside the last minute. The picture is almost hallucinatory. Modern civilization is not a mountain erected over a long foundation. It is a brief, bright spark on a cliff edge just before midnight. That perspective does two contradictory things to emotion. It makes existence seem impossible and miraculous in equal measure. On one hand, the odds against the precise chain of events that produced life, to say nothing of intelligence, feel astronomically remote. On the other, that improbability produces a feeling of uncanny privilege. To be alive now, in the narrow window when the universe is hospitable and the instruments to ask such questions exist, bestows a fragile honor. The question of origin, then, becomes personal in a way that is not narcissistic but reflective. The human mind, for a sliver of cosmic time, carries the capacity to turn its gaze backward toward the abyss. Yet the abyss is not only an absence of earlier times, it is also an eraser of traces. Deep time is a patient, relentless sculptor. The planet wears geological processes like a slow film that rewrites its surface. Tectonic plates shift continents as if they were pages being shuffled. Oceans swallow up coasts and grind unto dust. Mountains rise and crumble in cycles that span epochs. Even the most durable artifacts, stone, metal, ceramics, are vulnerable when stacked against millions or billions of years. Erosion can turn a city into sediment. Chemical weathering can leach stratified records into chemical soups where meaning is lost. Fossils, for all their drama when discovered, are rare imprints in a vast, indifferent archive. This reality opens a speculative doorway which is both intoxicating and unnerving. If the planet is a palimpsest, the writing of one era scraped clean to serve another, then how confident can any civilization be about its own place in the sequence? Could there have been other intelligent societies long before the one that shaped this present moment? The question has the rhetorical power of a mystery thriller. Its premises are plausible enough to spark curiosity, but the available evidence is dolorously thin. The mind trained by documentary skepticism weighs the odds with care. Civilization leaves signatures: urban geometry, isotopic anomalies, large-scale mining, synthetic molecules that do not occur in nature. Yet the durability of such signatures over geological timescales is doubtful. Organic compounds degrade, metallurgy may melt and disperse, synthetic isotopes decay. The window for unambiguous detection narrows as the timescale stretches. Geological activity will fold, bury, and recycle crust. Any candidate for ancient artistry or industry must have been monumental both in scale and in the permanence of its materials to survive 500 million years, let alone billions. It is here that the speculative and the scientific perform a complex dance. To imagine an ancient civilization is to engage with the mechanisms of erasure and preservation simultaneously. One can picture a city-state the size of a continent, its infrastructure carved into bedrock and alloyed with materials resistant to chemical weathering. One can imagine its monuments standing like black monoliths against the slow rush of time. But the imagination must then counterpose this with hard facts. Plate tectonics faults continents into new continents. Steep sedimentation buries the ruins under kilometers of new material. Mountain building uplifts and then grinds down the remnants. The planet is not a museum. It is a manufacturing floor where old objects are raw material for the next generation of strata. Emotionally, this confrontation produces a strain that is neither purely despairing nor purely hopeful. It is the same knot that tightened around earlier questions of origin, a recognition of smallness, and a resolve to examine the world closely nonetheless. If traces are fragile, then the work of looking becomes more urgent, more patient, and more creative. If evidence is likely to be subtle, the discipline of inference must become more sophisticated, attuned to whispers rather than shouts. The modern scientific method, with its appetite for residuals, pattern and isotopes, anomalies in sediment layers, peculiar distributions of rare elements, answers that call. Yet the process never purports to be conclusive in the sweeping way that myth once promised. It accepts provisionality and crowns it with humility. There is a moral dimension that creeps into the question of origins. For those who contemplate a beginning as a single event, there is an implicit invitation to examine beginnings in others, the beginnings of ecosystems, technologies, languages, and moral systems. Origins are not only cosmological hypotheses, they are narratives that give weight to action and purpose. To ask where the universe began is to be thrust into a meditation on care. If everything is ephemeral and the past is fragile, then the present assumes an ethical urgency. How will current choices ripple down, if they can ripple at all, through the narrow corridor of time humans occupy? The feeling is not necessarily burdening, it is galvanizing. Knowledge of finitude can sharpen the sense of responsibility. A documentary voice that dwells on these themes must balance the seduction of the question with the sober charm of evidence. It cannot trade mystique for mysticism, nor can it be lured into certainties the data do not support. It can, however, linger in the middle distance where wonder and skepticism meet. It can translate the deep mathematics of cosmology into the communal language of feeling without reducing the science, and it can allow speculation about vanished civilizations to remain speculative, provocative, instructive, but not declarative. This boundary setting matters because the opening question radiates consequences. If the origin is a single event, then structure and chance are braided in a particular way. Cosmic history becomes a narrative, where initial conditions matter intensely, but where subsequent dynamics also sculpt fate. If, by contrast, the origin concept fractures into an ensemble of processes, if time is cyclical or multiversal, then the emotional stakes shift. The horror of absolute beginnings softens, replaced by a staggered choreography of innumerable births and deaths. Each model reframes human significance, even if it does not alter that small, private sensation of awe. The immediate emotional reaction to the original question is often the same: a stunned quiet. The human mind, accustomed to moving from one task to another with fluent competence, must pause to accommodate the scale of the inquiry. It is in that pause that stories collect themselves, ancient myths, the cool graphs of cosmology, the geological record with its mute but eloquent layers. The pause is not empty, it is a crucible. The narrator's voice in a documentary may lower and lengthen, as if to keep the listener inside the moment. The language will turn to images: a single candle in a cathedral, a single breath at the edge of a cliff, a photograph of Earth taken from a lunar distance where continents and oceans merge into an improbable jewel. These images will be small-scale analogues for the cosmic single-point origin, devices that aim to conjure the unimaginable by comparing it to the intimately known. The section must close not with finality but with a hinge. The shock of the question primes the audience for a journey through observation, through the archives of the planet, and through cautious imagination. It sets the emotional temperature: high curiosity, tempered awe, a sliver of anxiety, and a persistent ethical curiosity. The opening asks for patience. It insists that subsequent investigation will be methodical and imaginative in equal measure. It promises to follow traces where they lead, to the relics embedded in rock, to the subtle signals in deep time, and to the models that attempt, with exquisite humility, to reconstruct the earliest moments of everything. In that sense, the question is less an accusation than an invitation. It invites the listener to step back from immediate concerns and to consider scale. It invites careful looking at what remains and disciplined speculation about what could have been. It invites an emotional posture that is receptive rather than triumphant, to feel small, certainly, but also connected, compelled, and curiously potent, the kind of potency that arises when a species, cognizant of its fragility, chooses to investigate the great unknowns with wonder and rigor. Where did the universe begin? The question will not be answered in a single narrative, nor is it intended to be. It is the first note in a long composition, one that will probe the Earth's deep archives, the echoes of ancient light, and the possibilities that lie in what has been forgotten. The opening is a promise to follow method where it can, to hold speculation where it cannot, and to keep the human response, fear, awe, curiosity, at the center of the story, because it is those responses, more than equations, that have propelled the search from the beginning. 2. Big Bang, the moment of birth. What does it mean to speak of a beginning when the very language of before and after unravels? The question is a thin blade, cutting through ordinary intuition and exposing a peculiarly fragile place, the instant where time itself first took a step. It is less a scene than a paradox. To imagine that all that ever was, distance, duration, the possibility of change, was once packed into an unthinkably small, hot, and dense condition, is to confront an origin that looks less like a beginning of things and more like the universe taking its first breath. In that first breath, the cosmos did not arrive as a gentle sunrise. It erupted, not in the romantic sense of a cathedral thunder, but as a mathematical and physical event that reshaped the grammar of reality. The term Big Bang is clumsy, a popular label that flattens complexity into a single image, yet beneath the slang lies a sequence of transformations so rapid and violent that human metaphors strain. Within a sliver of time shorter than the blink of a thought, far shorter than any human construct of measurement, space swelled and stretched, and energy condensed into the first quanta of matter. The early moments resist ordinary comparison, so the imagination is forced to borrow from analogies. Consider a tightly coiled spring that, once released, expands not outward into empty space, but creates the space into which it expands. Or imagine the surface of a balloon inflating so quickly that the distances between points on its skin multiply faster than any single point can track. These images are imperfect. They humanize a process that was impersonal and absolute, but they serve the necessary purpose of translating scale into texture. The universe, for its earliest fractions of a second, was not a venue within which things happened. It was the event that made happening possible. Physicists mark a sequence. In the first trillionth of a trillionth of a trillionth of a second, the Planck epoch, known physics dissolves into speculation. Quantum gravity, still a name with unfinished definitions, rules. After that, inflation takes over, an epoch of exponential expansion during which space multiplied its size by factors that stagger the mind. What had been microscopically confined swelled to macroscopic proportions in a heartbeat. Inflation is the universe's early amplification, a mechanism that stretched quantum jitters into the seeds of everything to come. Tiny fluctuations, mere ripples in a primordial field, became the density contrast that, billions of years later, would gather into stars and galaxies. As the cosmic fabric cooled, energy began to transmute into particles, a quark-gluon plasma, an incandescent, viscous broth where quarks and gluons freely roamed, filled the newborn universe. The metaphor here is of a seething ocean, too hot for bound structures to exist. Quarks, the component parts of protons and neutrons, were transient shivers in this plasma. Only as expansion cooled the soup could these constituents clamp together, forming the first hadrons. Seconds to minutes after the initial surge, protons and neutrons found mutual affinity. Nuclear reactions began. Light elements were forged in a brief, furious choreography known as Big Bang nucleosynthesis. Within roughly 3 minutes, hydrogen, helium, and trace elements emerged, their proportions imprinted by the precise balance of expansion rate and particle physics. Those early nuclear recipes were unforgiving. Change one parameter, the density of baryons, the number of neutrino species, the rate of expansion, and the elemental yield shifts. That delicate balance is part of the deeper emotional resonance of the origin, the cosmos, in its infancy, negotiated a narrow set of conditions that allowed chemistry to be possible. The universe could have been otherwise. Instead, it threaded a narrow channel where atoms later formed, molecules later assembled, and, billions of years hence, planets cooled. But the orchestra of creation kept playing beyond nucleosynthesis. For hundreds of thousands of years, the universe remained a fog. Photons, the carriers of light, were trapped, scattering off free electrons in an opaque plasma. No clear vision could be had. Radiation and matter were welded in an intimate, noisy dance. Then, about 380,000 years later, as the temperature fell to a few thousand kelvins, electrons combined with nuclei to make neutral atoms. The fog lifted. Photons escaped and began their long sojourn across expanding space. Those photons are still detectable today as the cosmic microwave background, the afterglow of the origin stretched into microwaves. By cosmic expansion, it is the most ancient message we can intercept, a fossil of the universe's youthful furnace, washed smooth but rich with a whisper of the earlier structure. That afterglow is strikingly uniform, but it bears the faint signatures of those inflation-amplified quantum ripples. Tiny temperature anisotropies, parts in 100,000, mapped the seeds of future structure. Where the radiation was slightly cooler, matter would preferentially congregate. Where it was slightly warmer, it would thin. Through gravitational attraction and billions of years of accretion, those spots of statistical favor became filaments, halos, galaxies, and the hierarchical lattice astronomers now map across the sky. The story from anisotropies to galaxies is long, patient, and non-violent in human terms. It is the slow accumulation of chance and attraction. In telling this, one must not fall into a false narrative of inevitability. The transition from the homogeneous, near-featureless fireball to a cosmos of islands of light and dark is contingent. Contingent on the initial spectrum of fluctuations, on the physics of dark matter whose nature remains elusive, and on the interplay of cooling, feedback, and star formation. If inflation's amplitude had been slightly different, or if dark matter interacted differently, the morphology of cosmic structure could be wholly unlike what observers see. The once-and-for-all parameter choices of the early universe determine, with an economy that belies comprehension, the tapestry of future possibility. And yet, against that extraordinary scale, there is an intimate human response. The listener, in the narrow temporal window when intelligence can ask these questions, feels both absurd and privileged. The origin narrative produces an ambivalence of feeling. There is a sense of cosmic indifference. The initial conditions were impersonal, not arranged for particular outcomes. But there is also wonder that from these impersonal rules emerged enough stability and complexity to allow observers to form who could look back, parse the microwave whisper, and reconstruct a credible chain of events. The mind oscillates between the cold arithmetic of physics and a warm impression of being part of a rare, beautiful sequence. This balance between contingency and pattern is more than philosophical musing. It becomes a methodological caution when moving forward into the planet's history and the possibility of past intelligences. The same precision-seeking whispers in a faint background, sorting signal from noise that cosmologists apply to the early universe, will serve those who probe Earth's deep time. If the cosmic beginning shows how swiftly potential can be stamped into reality, it also teaches how fragile the record of that potential can be. Consider the kinds of relics the Big Bang actually left behind. Radiation is the salient survivor at cosmic scales. But on planetary scales, the survivors are much fewer and far more vulnerable. The provenance of elements: hydrogen, helium, traces of lithium laid down in the first minutes provided the raw materials for later chemistry. Heavier elements, forged later in stars and dispersed by supernovae, furnish the building blocks for planets and life. The origin thus establishes a chain. Early nucleosynthesis sets a baseline. Stellar alchemy enriches galaxies. Planetary assembly concentrates materials into habitable locales. Each stage is a filter. What survives is what the physics and chemistry allow. This chain has a consequence the narrator cannot ignore. If humanity asks whether a civilization could have arisen and vanished long before continents assumed their present arrangements, they must reckon with the origins lesson. Time and mechanism are blunt tools. Even if lifelike processes can emerge wherever conditions permit, the record of them is subject to the erosive power of subsequent epochs. A planetary crust can be recycled into mantle, oceans can open and close, atmospheres can change. The universe offers memory in the form of radiation and element abundance, but not detailed cultural artifacts. The cosmic inception favored the formation of atoms and then stars. It did not secure the permanence of their later arrangements. Yet there is another kind of survival hidden in the Big Bang's narrative, one that is subtle and profound. The laws and constants that govern that first instant have also governed the unfolding of increasing complexity. The predictability and regularity of physical law are the scaffolding on which long-term memory and cumulative processes rest. Stable causality makes possible the accumulation of structures over eons. Molecules can assemble into self-replicating patterns. Ecosystems can adjust and preserve functional arrangements. Technologies, once attained, can be refined and transmitted. The universe's beginning, then, is not merely a point of ignition, but a commitment to reproducible rules. That reproducibility is what allows the improbable to be rehearsed enough times that something like intelligence, capable of reflecting on origins, may appear. The narration here must keep a cautious voice. Scientific humility resists romanticizing the Big Bang as an act with purpose. The origin is not an artisan's plan. It is a physical series of conditions from which complexity can, under fortunate circumstances, arise. But the contours of that series matter. The early expansion rate, the types and abundances of particles, the presence of dark matter and dark energy, each element shapes the long-term dynamics that would determine whether the cosmos is mostly empty or occasionally hospitable. Each parameter is a line in a vast contingency table. There is a narrative economy worth noting. Cosmic history, from the Big Bang to the forging of the first stars, occupies less time than the intervening stretch through which observers arise to ponder it. That compresses the feeling of origin into a brief overture. It is as though a symphony's first movement, fast and concentrated, dictates the harmonic possibilities for movements yet to come. Listeners in the final movement can still detect the motifs introduced at the start. The faintness of the microwave background is this music's last lingering chord. As the story of the origin closes, the voice must pivot gently toward Earth's subsequent history, for the cosmic debut is the prologue to a much longer, more intimate chronicle. The universe's birth set the stage. It produced a periodic table, distributed matter into clumps, and allowed gravity to sculpt systems where planets could form. Yet the specific architecture of the solar system, the chemical inventory of early Earth, and the geological processes that would either preserve or erase later artifacts are local outcomes of processes seeded by the origin. The narrator can now ask, with renewed poignancy, given how the cosmos began, what kinds of traces might persist over deep time on a planet like ours, and leaning into the central speculative motif of this documentary, could those traces ever hint at a civilization that rose and was scrubbed away by the slow mechanics of geology and climate? That question forms the hinge into the next section. The Big Bang supplies the cosmos's primordial palette. The strokes that follow are painted on planetary canvases with tools that are more random, more violent, and in some ways more fragile. The listener senses a tonal shift from the impersonal ballet of physics to the messy contingent theater of planetary affairs. But the memory of the origin remains. It is encoded in the abundances of atoms, in the fossil microwave light, and in the regularities that enable cause and effect. Those elements are the archaeologists' first map when they descend into deep time. 3. Njong. What is the smallest thing that can be called a thing? It is a question that folds inward on itself, the kind that feels simple until one begins to measure the scales and finds the ground missing. The earliest history of reality offers an answer that is both stark and prosaic. Things begin as relationships, patterns of energy and rule, before they ever look like objects. In the first instance after the cosmic origin, what would later be named proton, neutron, and electron did not arrive as ready-made beads on a string. They were emergent actors in a drama of cooling, symmetry breaking, and chance. To tell that story is to trace how the universe learned to hold on to structure at all. The first fractions of a second are not an arena of leisurely formation. They are a crucible in which conservation laws, quantum fields, and the peculiar interplay of forces decide what is possible. Within the ephemeral Planck epoch and the immediate cascade after it, the universe was unimaginably hot and dense, so compact that the familiar distinctions of space and time begin to blur. In that environment, the concept of a particle is not yet a stable identity. It is instead a resonance, a temporary solution to the conflicting demands of quantum fields. As the expansion proceeds and temperature falls, those resonances can lock into durable patterns. Quarks, the constituents of protons and neutrons, first existed as free, almost fugitive excitations in a viscous, radiant soup. The early universe was filled with a quark-gluon plasma, a roiling medium where quarks and the carriers of the strong force, gluons, moved with little constraint. The imagery that serves the imagination best is kinetic rather than visual. It is the sense of an environment too energetic for binding, where everything that tries to hold together dissolves under the onslaught of thermal motion. Only as the universe expanded and cooled did the strong force begin to confine quarks into composite structures. In a matter of microseconds after the initial surge, quarks found companionship. Groups of three bonded into baryons, protons and neutrons, while pairs formed mesons that flared and fell away. This transition confinement is subtle in physics, but enormous in cosmic consequence. The appearance of protons and neutrons provides the scaffolding for atomic nuclei. It marks the shift from an undifferentiated field to a universe where discrete particles carry rest mass and can persist long, enough to become ingredients for atoms. The transition is also messy. The early balance between matter and antimatter, between baryons and their antis, was not perfectly neutral. A faint asymmetry tipped the scales. That tiny imbalance, a whisper in the uniformity, is the reason there is anything left to form atoms with at all. If matter and antimatter had been precisely equal, annihilation would have left a near-empty sea of photons. Instead, the surviving sliver of matter would later clump, cool, and give rise to chemistry. The origin story here carries a moral of contingency. Cosmic architecture depends on asymmetries so delicate that they could be interpreted as luck. Electrons, unlike protons and neutrons, are leptons, particles that do not participate in the strong force. Their appearance in the early universe is tied to the same thermal history but follows a distinct arc. High-energy collisions created and annihilated electrons and positrons in a furious interchange. As temperature dropped, production became unfavorable. Annihilation dominated, depositing energy back into the radiation field. The electrons that remained were the companions to the positively charged protons, ready in much later epochs to orbit nuclei and make atoms. Observers looking back from a cosmic distance see in that persistence a kind of promise. The universe now possessed two fundamental ingredients, massive nuclei and light, mobile electrons, without which chemistry as it is known could not unfold. The formation of neutrons and protons is also a tale of time-sensitive transforms. Protons and neutrons interconvert through weak interactions, and the rate of conversion depends on ambient temperature. As expansion lowers the temperature, the weak interactions freeze out. The relative abundances between protons and neutrons become locked. Thereafter, free neutrons begin to decay unless they are quickly conscripted into nuclei. In the few crucial minutes after the Big Bang, a brief period of nucleosynthesis played out. Protons and neutrons fused to create the first light nuclei, principally hydrogen and helium with traces of deuterium and lithium. The proportions were not arbitrary. They were set by reaction rates, the density of baryons, and the expansion history. The composition produced in that brief window, roughly 3/4 hydrogen to 1/4 helium by mass, would be the baseline. Chemistry available for star formation and for the later material chemistry of planets. The mood that accompanies this phase of cosmic history is peculiar. There is an austerity to it, an almost clinical minimalism. In human terms, the universe seems to have made conservative bets. It produced mostly hydrogen and helium, elements that are simple yet fertile. Those bets set constraints on what planetary chemistries could later be realized. They are the alphabet from which later chemical words must be spelled. The insistence of physics toward economy, toward a narrow suite of initial building blocks, creates a tension between possibility and limitation. The emotion that arises in the observer is not wonder alone, but a reflective curiosity. How much of the future is already hinted at in these elemental imprints? The narrative of particles arriving continues into the epoch of transparency, and there the story shifts tone. For hundreds of thousands of years after nucleosynthesis, the universe remained a diffuse but opaque fog. Photons were imprisoned by free electrons, scattering incessantly in a bright, seething plasma. Light could not travel far without being turned aside. The universe was a luminous stew in which visibility was local and ephemeral. Then, as expansion cooled the cosmic temperature to a few thousand kelvins, a fundamental change occurred. Electrons lost the thermal vigor that kept them free. They were captured by nuclei to form neutral atoms. This recombination, misleading in its name, for electrons were combining for the first time, altered the interaction between matter and radiation profoundly. When electrons bound into atoms, photons found the medium suddenly far more transparent. The dense fog lifted. For the first time, light could stream across vast distances, no longer trapped in endless scatter. This moment is often described as the universe's first breath of clear light, the epoch of last scattering, roughly 380. Zound years after the beginning. The photons released at that time have been traveling ever since, chilled and stretched by the expansion of space, now visible to modern instruments as the cosmic microwave background. They are a fossil, an imprint of the conditions at the surface of last scattering, a map of tiny fluctuations in temperature and density that were seeded by the earlier quantum ripples. That first light is more than a technical relic. It is temporally and emotionally resonant in a documentary sense because it marks the universe's first coherent long-range communication. Nothing before had been capable of sending an undistorted message across such distances. Before recombination, any photonic whisper was immediately drowned by scattering. Afterward, information could be preserved and transmitted. The cosmic microwave background is a message in a bottle, thrown outward at the moment, a medium allowed its drift, carrying information about the primordial conditions. Modern observers interpret its mottled pattern, anisotropies of parts in 10,000, as the fingerprints of those initial perturbations that would later grow into galaxies. The first light, therefore, is both revelation and prophecy. It reveals the past and prophesies the structure of the future. The imagery that helps make sense of this shift is domestic rather than cosmic. It is as if a thick fog had obscured a landscape for all time and then suddenly parted. For the first time, distant shapes and elevations came into view. Oh! The listener in the here and now feels a kinship with that first seeing. It is a primordial clarity, a rare instance when the universe made a visible record of itself. Yet the record is patchy. The surface of last scattering is a two-dimensional screen that encodes primordial conditions, but contains no direct narrative of later, local events, no story of planets, no signatures of life, no urban geometries. It is a map of the soil conditions for future growth, not an atlas of civilizations. The first light also changes the tone of causality. Up to recombination, the dynamical interplay between radiation and matter strongly regulated the growth of perturbations. Photons exert pressure, they resist collapse. After transparency, gravity could act with greater freedom, permitting density fluctuations to amplify. A time of slow accretion began, spanning millions and then billions of years. The universe, which had spent its earliest ages in acts of intense global transformation, receded into a long patience. Stars ignited, galaxies coagulated, and the alchemy of stellar interiors forged heavier elements. Yet the possibility of complex chemistry and, eventually, of planetary systems was rooted in the structural seeds and elemental starting points produced earlier. There is a moral of attenuation to this arc. The formations of protons, neutrons, and electrons, and the later liberation of the first light are events whose implications trickle forward. They shape what is possible, but do not determine every detail. The cosmos arranges a set of permits rather than scripts. From a documentary vantage, this is a useful humility. It suggests that grand beginnings do not guarantee particular futures. They only provide the substrate upon which contingency plays out. The first particles supplied atoms, and the first photons supplied a cosmic ledger. What follows depends on innumerable subsequent accidents and iterative processes. For those contemplating deep time mysteries, such as whether earlier intelligent societies might have arisen and left traces, the events of the first seconds and the first light set an important context. The elemental proportions resulting from early nucleosynthesis determine what materials will be available for planet formation. And for any hypothetical technology, the early transparency establishes the scale at which primordial structure can be inferred, but it does not by itself preserve detailed cultural information. In other words, the foundational physics offers constraints and possibilities, but provides little direct evidence for local, later affairs. That recognition frames both wonder and restraint. There is wonder in contemplating that a handful of physical rules, acting over unimaginable scales of temperature and duration, can produce atoms and the first transparent light. There is restraint because those same rules remind the thinker that permanence is rare. At the larger scales, radiation preserves a pale memory. At local scales, geology, erosion, and chaos are indifferent editors, often rewriting or erasing what fragile inscribers of culture might leave. The voice of the documentary, then, carries a double responsibility: to celebrate the profound elegance of these earliest acts and to caution against grand extrapolations where evidence will not support them. The history of protons, neutrons, and electrons is not a narrative of inevitable progress toward life or intelligence. It is rather a saga of enabling conditions. The first light taught the cosmos to keep a durable, if partial, archive in photons. The particles taught matter to clump and endure long enough for complexity to emerge. Together they created a stage. On that stage, countless performances, galaxies, stars, planets, perhaps civilizations could be attempted, some briefly, some persistently. But whether any particular performance leaves a visible, unambiguous trace across hundreds of millions or billions of years remains a question that will be explored not by poetic assertion, but by careful, patient examination of the planet's own stratigraphy. In the hush following these early acts, the universe shifted into a slower kind of narrative. The furnace cooled, structures emerged, photons carried a memory of the first visual field. Those photons became the oldest light that can be intercepted, and within them lies an invitation to read the patterns, to reconstruct the scaffolding on which later complexity rests. For an audience considering deep time and erased civilizations, that invitation is as practical as it is philosophical. The first particles and the first light are the foundation stones. They are not the whole edifice. But without them, nothing all the later conjectures could rest upon would be possible. What does it mean for the universe to stop hiding? That is the question that hangs at the opening of this chapter. Not a picture of floating gas or a romantic sunrise, but the idea of transparency itself, the moment when light first became a messenger rather than a prisoner. In that instant, the cosmos converted a hot, impenetrable fog into a record, a faint and enduring fingerprint that would travel unscathed across eons. That fingerprint became the cosmic microwave background, and it is both a relic and a promise, a whisper from an era before stars, a map of possibility, and the first long-distance conversation the universe ever allowed. The chemistry of that conversation begins with cooling. In the furnace of the early cosmos, energy and matter were tightly coupled. Photons dragged electrons along like restless children, scattering from charged particles so often that any notion of a straight path was meaningless. For hundreds of thousands of years, the universe was a bright, opaque stew hot, dense and uniform to an astonishing degree. Then, as expansion did its steady work and the ambient temperature dropped, electrons found rest. They were captured by nuclei to form neutral atoms. In a breath that no human ear could hear, the scattering faded. Light, suddenly freed, streamed outward for the first time without being constantly scattered back into the fire. Those photons have been traveling ever since. Their wavelengths were stretched by the expansion of space itself until what was once visible, light, now glows as microwaves. The cosmic microwave background, CMB, that modern instruments detect, is not a picture in the ordinary sense. It is a thin, mottled screen of temperature differences, a two-dimensional fossil of the universe at an age of mere hundreds of thousands of years. Its uniformity is striking, its small fluctuations are crucial. Embedded within those tiny anisotropies, departures from perfect smoothness at the level of 1 part in 100,000 were the seeds of all later structure. Where the radiation was imperceptibly cooler, slightly denser regions of matter would begin to win a slow gravitational contest. Where it was a little warmer, matter would lag behind. Those initial inequalities, inflated from quantum jitters in the earliest moments, mapped where the first clumps would form. To a human mind attuned to stories, the release of the CMB is an almost cinematic reversal, an opaque universe becoming legible, like a manuscript whose letters take shape. But the record it carries is coy. It tells of density and rhythm, of scales and spectra, of the primordial orchestra's notes. But it offers no narrative of local affairs. The CMB cannot tell whether life will arise, whether planets will form with complex chemistry, or whether intelligence will one day read the light. It encodes a foundation, a distribution of potential, not a final script. From that foundation, the universe set about building lighthouses. For a long time after recombination, matter was diffuse and cold by earlier standards. Gravity, patient and indifferent, began to draw slight overdensities into deeper wells. Dark matter, an invisible scaffolding that neither emits nor absorbs light yet outnumbers ordinary matter, played the decisive role. In this architecture, it clumped first, creating halos whose gravitational pull would shepherd baryonic gas. The baryons fell into these wells, compressing and heating as they accreted. Over tens to hundreds of millions of years, the slow emergence of structure unfolded, filaments and nodes in a cosmic web. Knots where matter pooled and the first stars would ignite. The birth of the first stars is a drama of extremes. These were not placid, long-lived suns like the sun that would later host a temperate planet. They were, in theoretical expectation, behemoths. Population 3 stars formed from pristine hydrogen and helium produced in the Big Bang. Without heavier elements to provide efficient cooling, the collapsing gas clouds remain warmer and more resistive to fragmentation. Gas fragments into stars more readily when it can radiate away energy, which metals and dust facilitate. In the metal-free primordial gas, cooling was less effective. Gravity had to gather larger masses before collapse produced the densities required for nuclear ignition. The result, models suggest, were stars tens to hundreds of times the mass of the sun, short-lived, furious furnaces that burned bright and died quickly. Imagine a universe that had been in darkness for hundreds of millions of years. Then, in pockets, titanic furnaces flare into existence, thousands, perhaps millions of solar masses collapsing into a single incandescent point. The first flashes of starlight pierced the cosmic night like flares. Their ultraviolet radiation ionized the surrounding hydrogen, carving out bubbles of ionized gas and beginning the epoch of reionization, a phase change in which the intergalactic medium rekindled as transparent plasma from being neutral. This was not a gentle enlightenment. It was a riotous, patchy process in which the first stars, galaxies, and accreting black holes bathed their neighborhoods in energetic photons, sculpting the medium and terminating the universe's dark ages. The fate of these early titans was violent. Their cores fused lighter elements into heavier ones, and then, depending on mass, they ended in explosive deaths. Pair instability supernovae, theorized to have been common among extremely massive population 3 stars, would have unbound the star entirely, casting newly forged elements into the surroundings without leaving behind a compact remnant. Other massive stars collapsed into black holes, seeding the cosmos with dark, compact objects that would later grow into the supermassive beasts anchoring galactic centers. The supernovae were crucibles and dispersers within their blasts. Carbon, oxygen, silicon, iron, what astronomers call metals, were synthesized and scattered into the interstellar medium. These metals would change the rules of star formation. They provided new channels for cooling, allowed gas clouds to fragment into smaller masses, and made possible a later generation of long-lived, metal-enriched stars, and eventually planets with the chemical complexity necessary for chemistry as we think of it. The emotional cadence of these transitions is double-edged. On one hand, there is exhilaration in the first light's arrival and the cosmic transmutation that follows, a sense that the universe had crossed a threshold from potential to diverse actuality. On the other hand, there is an acute awareness of contingency. The chemistry that enables planets and life required the deaths of giants, rare events in the early universe's history. If the first generation of stars were few or formed differently, the timing and abundance of heavy elements would change. The emergence of rocky worlds capable of supporting long chemical histories is contingent on that early enrichment. The narrator's voice in a documentary can linger on this paradox. The universe was at once fecund and precarious, capable of forging complexity, yet susceptible to delays and constraints imposed by the initial distribution of matter, and the efficiency of early star formation. As galaxies assembled from the hierarchical merging of smaller proto-galaxies and gas clouds, the cosmic landscape grew richer and more varied. Some regions would host vigorous starbursts, converting gas into stars at furious rates. Others would be more sedate, forming stars over protracted epochs. The interplay between radiation pressure, supernova-driven winds, and the gravitational pull of dark matter shaped the morphologies of early galaxies. Small, irregular clumps coalesced into larger structures. Disks and spheroids emerged. Central black holes accreted mass and became luminous quasars that could outshine whole galaxies. The first galaxies were both the forges of elements and the crucibles of environment sites where the conditions for later planetary systems were decided. If the documentary voice seeks tension, it finds it here. The early universe was creative but ruthless. Heavy elements were necessary for planets and chemistry, but the same processes that produced those elements could sterilize or sweep them away. Intense ultraviolet fields could dissociate molecules. Supernova shocks could disrupt star-forming clouds. The timeline for habitability, when and where sufficiently metal-rich and dynamically calm environments could exist, was not universal. Instead, pockets of potential emerged unevenly across the cosmic web. For any speculative thought about ancient technological civilizations elsewhere in the universe, this sequence imposes a hard minimum. No complex chemistry and no solid planets could exist before the first stars lived and died. The earliest possible window for rocky world formation opens only after a generation of stellar alchemy has seeded the interstellar medium. There is also a profound lesson about memory. The first stars created the elements that would later be built into planets and perhaps tools, but their own imprint on the record takes unusual forms. On cosmological scales, they contributed to the reionization signature detectable in the polarization of the CMB and in the absorption signature seen in the spectra of distant quasars. On local scales, their metal yields mixed into nascent clouds that would form second-generation stars. But if an advanced intelligence had arisen in some isolated eddy of this early cosmic stream and erected monuments of stone and alloy, would those monuments survive the storms of cosmological time? The narrator must balance the drama of starbursts with the sober physics of preservation. Erosion operates on planets, tectonics recycles crust into mantle, ocean chemistry dissolves surface artifacts. The universe gives and it takes away. The narrative reaches a crest with the realization that the elements forged by the early stars became the raw vocabulary of planetary chemistry. Carbon's versatile bonding, oxygen's role in water and silicates, silicon and magnesium's structural importance for rocks, all were produced in stellar interiors. The fingerprint of those processes is visible in abundance patterns across the galaxy. Heavier elements are more plentiful in regions that have experienced many generations of star formation. In this way, cosmic history writes its story into the chemistry of worlds. A planet that forms in a region enriched by several stellar generations begins life with a richer toolkit for complexity, a fact with direct implications for any hypothesis about ancient civilizations. The earliest epochs set the earliest deadlines. Life, and thus civilization, can only begin its speculative journey once the necessary raw materials exist in abundance and remain available in stable environments. Throughout this cosmic unfolding, the CMB remains an indispensable compass. It is not merely a relic from a forgotten morning, it is an empirical map whose tiny fluctuations predicted precisely the large-scale structure astronomers later observed when telescopes later scanned the microwave sky. When spectrographs dissected light from the most distant quasars and the faint glow of ancient galaxies, the early anisotropies resolved into a coherent story. Quantum perturbations inflated, dark matter gathered, gas fell into halos, stars ignited, and the complex web grew. That coherence is emotionally satisfying. It is the rare case in science where the universe's earliest whispers and its later structures speak the same language, yet at every step there is a counter-voice of doubt and humility. The processes that produce stars and galaxies are non-linear and often chaotic. Small changes in initial conditions or microphysics can cascade into very different outcomes. Models of population 3 stars are still partly conjectural. The precise masses, lifetimes, and numbers remain areas of active research. Observationally, astronomers push telescopes to the limit, seeking the faint glow of the earliest galaxies and the spectral fingerprints of primordial chemistry. Each new observation sharpens the narrative, but also reveals complexity and surprise. For the listener, the emotional thread is twofold: a sense of privilege and a sense of ephemerality. The universe's transition from opacity to light, from simple elements to the chemistry of life, is a slow miracle, an accumulation of fragile contingencies played out over hundreds of millions of years. That miracle enabled everything that follows, including the possibility that some intelligence might one day look outward and reconstruct the tale. But it also underlines how transient the physical records of such intelligence would be on cosmic timescales. The stars that made the elements did so in blasts and winds. The planets that gathered them are subject to erosion and plate tectonics. Atmospheres evolve and can erase biosignals. If there were any earlier civilizations in the universe on planets circling second-generation stars or in now vanished pockets, their tracks might be diffuse, their signatures faint whispers overlaid on more dominant geological and astrophysical processes. As the chapter closes, the narrative pivots toward a narrower, more intimate canvas, the solar system and Earth. The dawn of stars seeded the cosmos with the ingredients for rocky planets. The sun itself is a product of generations of stellar evolution, and Earth's inventory of elements bears the memory of those earlier fires. The story of the CMB and the first stars provides the broad cosmological scaffolding. The next movement will examine how, on a particular planetary stage, our planet, those scaffolding pieces were assembled into the environments that could host life and, eventually, reflective minds. The listener is left in a charged silence. The universe turned on its first lights, spread the raw materials, and in doing so, wrote a promise into the fabric of space. Whether that promise culminated in civilizations long since erased, or whether it waits for futures yet to come, is the question that follows. What is the sound of a universe turning on its lights? The question is not rhetorical, it is a probe into the quality of suddenness and consequence. Before those first flames flared, the cosmos was a deep, slow, dark, an ocean of near-uniform gas. A faint echo of the first breath stretched thin by expansion. Then gravity, that patient, indifferent law, began to gather what was loose. The process was not theatrical in a human sense. It was slow tectonics writ across cosmic expanses. Yet the aggregate effect was dramatic. Isolated dimples in density became wells, and those wells, over tens to hundreds of millions of years, became arenas where the first stars were born. The universe, which until then had only permitted whispers, allowed concentrated shouts. Gravity is the unromantic craftsman of structure. In the aftermath of the primordial ripples, those minuscule differences in density imprinted on the cosmic microwave. Background dark matter gathered first. Invisible and unreactive to light, dark matter acted like an invisible scaffolding, a skeletal mesh that set the stage. Baryonic gas, hydrogen, and helium in overwhelming abundance followed where the scaffolding cupped it. Gas fell into the dark matter halos, converting potential energy into heat. For a time, that heat resisted further collapse. Pressure fought gravity, radiation pushed back. What changed was not a single event, but the slow availability of cooling channels. Cooling is the secret skill of the universe when it decides to make compact things. In the metal-poor, dustless conditions of the early cosmos, cooling had to be achieved with the slenderest of tools. Molecular hydrogen, the simplest molecule, became the cool hand that allowed clouds to lose heat and fragment. H2 formed inefficiently and in small amounts, but where it did form, it permitted a cloud to radiate away energy and contract further. Without heavier elements, carbon, oxygen, silicon, to act as efficient radiators and to seed dust that aids thermal escape, collapsing gas tended to remain hotter and thus to form larger fragments. The consequence, according to theoretical models, was an early stellar population unlike the steady, long-lived stars that later embellished the galaxy. These first stars, labeled Population 3 by astronomers, were likely beacons of extremes, free from the cooling advantages of metals. Primordial clouds, probably cold masses tens to hundreds of times greater than that of the Sun before gravitational collapse, could produce the densities necessary for nuclear ignition. Such behemoths lived briefly and burned with an incandescent ferocity. Their internal engines fused hydrogen into helium and then onward into heavier nuclei in modes physically distinct from more metal-rich stars. Short lives yielded spectacular deaths, pair instability supernovae, and violent collapses that scattered fresh elements across. The surroundings were left behind compact black holes. The very processes that made later complexity possible were thus at once creative and destructive. The image of the first stars lighting the sky is cinematic but misleading if taken for romance. Those first flashes were isolated, like torches in a vast wilderness, not a smooth brightening. Reionization, the epoch when ultraviolet photons from these early sources ionized neutral hydrogen in the intergalactic medium, was patchy and protracted. Some regions, rich in early star formation or hosting accreting black holes, ionized their neighborhoods quickly. Others remained neutral for longer. Over a span of hundreds of millions of years, ionized bubbles grew, overlapped, and eventually transformed the cosmic fog into a transparent expanse again. The transition was messy, episodic, and driven by the competition between sources of ionization and the recombination of electrons onto protons. It was, in short, an uneven enlightenment. There is suspense in that unevenness. To a mind sculpted by human experience, the staggered brightening can be read as a story of interiors, pockets of rapid innovation surrounded by vast tracts of delay, islands of redoubt were the necessary catalysts. Density, cooling, a fortuitous confluence of merger events allowed the first luminous structures to ignite. Hierarchical assembly did the rest. Small halos merged into larger halos, proto-galaxies combined to create more substantial gravitational wells, and with more mass came deeper pools of gas and higher opportunities for sustained star formation. The nights of the early universe were punctuated with sudden flares and then quieter intervals. The rhythm was irregular, the era of first light, neither a single curtain rising nor a gentle dawn, but a complex choreography of creation and erasure. Supernovae from the first massive stars carried a different kind of drama. They were cosmic blacksmiths. In their final moments, these titans forged heavy elements, carbon, oxygen, silicon, iron, atoms not synthesized during primordial nucleosynthesis. Blast waves hurled this material into the interstellar medium, gradually enriching the gas with metals that would become crucial in later cooling and planet formation. The first dust grains formed in the cooling ejector of these explosions, themselves fragile and easily destroyed, yet decisive. Dust catalyzes the chemistry needed for molecule formation and enhances cooling pathways, making it possible for clouds to fragment into smaller masses. Where early supernovae enriched their neighborhoods, subsequent generations of stars could be smaller and longer lived, setting the stage for the kind of stellar stability that might someday support planets with prolonged habitability. Embedded in this chain is a stark lesson about contingency. The timing and efficiency of enrichment, how many early titans exploded, how their yields mixed into neighboring clouds, how winds and radiation redistributed material, determined when and where the ingredients for rocky planets would be sufficiently abundant. There was no guarantee that enrichment would be uniform or timely. In some regions, metal-poor conditions persisted, delaying the availability of planets with terrestrial material. In others, rapid recycling could seed robust metallicity in only a few generations. The cosmic tale, therefore, was not deterministic, but contingent, sculpted by stochastic processes that could tip local histories. In one direction or another, the formation of early galaxies added another layer of complexity. The cosmic web filaments of dark matter and baryons threading between voids acted like highways of mass transport. Gas streamed along filaments into the nodes where halos stacked and merged. Early galaxies were often small, turbulent, and gas-rich, irregular assemblages rather than the grand spiral and elliptical forms familiar later. Star formation within them could be explosive, triggered by mergers that compressed gas into dense knots. Some proto-galaxies produced luminous quasars when central black holes accreted material at furious rates, momentarily outshining the combined starlight of their hosts. These luminous beacons, observed as bright points at the limits of telescopes, suggest that massive black holes formed rapidly in some environments, an observation that raises theoretical puzzles about how such heavy objects could have assembled so early. The emotional undertone of this scientific unfolding is twofold. There is wonder and awe at the universe's capacity to produce diversity from humble beginnings, and a tightness of the chest at the fragility of the record. The physical processes that enabled the seeding of heavy elements were precisely those that could also erase local signatures. Supernovae blast apart nascent structures, intense radiation fields can dissociate molecules and heat gas. Out of shallow potential wells, winds can strip proto-disks of material. The same forces that manufacture complexity are also the forces of erasure. If the viewer contemplates whether any intelligence could have arisen during these earliest epochs, the scene looks inhospitable. Planets could not form before metals existed. Even where they later could, environmental volatility might have rendered stable, long-lived niches rare. Astrophysical reality thus frames speculative inquiry. If one asks whether ancient civilizations could have arisen and been erased by geologic time, the early stellar era imposes a necessary chronology. Any civilization preceding the era of universal enrichment would be impossible because the raw materials for rocky, chemically diverse planets simply did not exist. But the era that followed, populated by later generation stars and the first enriched galaxies, opened windows pockets of possibility. The problem is not impossibility, but preservation. The physical conditions that allowed early enrichment also ushered in processes that could quickly reshape planetary surfaces, strip atmospheres, and erase ephemeral constructions. Consider the question of memory. What might remain of a technological culture formed in those distant times on cosmic scales? Radiation betrays the existence of early star formation in global signatures. Reionization imprints on the cosmic microwave background. Certain absorption features in quasar spectra, the metallicity measured in ancient gas clouds. But material artifacts are more fragile. Geological processes on a planet, tectonic recycling, erosion, impact gardening, volcanism, operate over timescales that can obliterate surface structures within tens to hundreds of millions of years. Over a billion years, crusts can be subducted, continents renewed, atmospheres stripped and replenished. Even if a civilization had once raised monuments of stone or disseminated durable synthetic molecules into the environment, the chances of those signatures surviving intact for billions of years are slim, unless they were deliberately constructed at planetary scales or left isotopic fingerprints embedded deep within geologies, less prone to recycling. The early star's nucleosynthesis, however, offers a more enduring legibility, chemical abundance patterns. Certain isotopic ratios, unusual abundances of heavy elements, or the presence of short-lived radionuclides trapped in planetary interiors can be forensic markers. But interpreting such signals is not straightforward. Many natural processes can reproduce anomalies. Many astrophysical routes can seed planets with peculiar isotopic mixtures. Distinguishing a technological cause from a natural one requires extraordinary corroborative lines of evidence. The universe, in its openness, provides possibilities, but also plenty of plausible deniability. There is also another thread to pull: the seeding of black holes and the assembly of galaxy centers. Massive stellar deaths could produce remnants that later grow into supermassive black holes, the kind that power quasars. Those quasars, in turn, can shape the evolution of their host galaxies, regulating star formation by heating and expelling gas. In some scenarios, accreting black holes in the earliest galaxies could have produced such intense radiation that the surrounding interstellar medium was sterilized. The same central engine that signals early structure can be a purifying furnace. It is a recurrent motif in cosmic history. The agents of change are often the agents of destruction. Through these cosmic dramas, the narrative voice for a documentary seeks a balance. The telling must kindle wonder at the clarity of physical law and the extraordinary coherence of models that stitch quantum fluctuations to the architecture of galaxies. At the same time, it must emphasize humility. The deep time archive is noisy, partial, and often ambivalent. The first stars and galaxies were the universe's initial attempts at concentrated complexity. They succeeded in forging the elements and in making the cosmos a place where chemistry could happen. They also complicated the record, creating environments that are both creative and erosive. To an observer in the present, the early universe's history is both accessible and faint. Telescopes now probe light that left its sources when the cosmos was only a few 100 million years old. Spectra, luminosity functions, and absorption lines allow reconstruction of star formation rates and the timing of reionization. Yet every observation is a partial excavation of a far-off past, mediated by redshifts and cosmic expansion. The picture is progressively filling in, and with each new data point comes both confirmation and surprise. Unexpectedly bright galaxies, early quasars heavy with mass, traces of dust where none was predicted. The universe keeps teaching caution and interpretation even as it enlarges the canvas. In the end, the epoch of first stars and early galaxies is a prologue of concentrated potency. It is the moment when the cosmos transitioned from a fairly uniform field into a tapestry embroidered with complexity. The ancient titans forged the elemental alphabet. Their explosions sprinkled the ingredients for planets, life, and possibly intelligent agency. Yet those same processes set up conditions of fragility, dispersal, and erasure. The narrative that follows must reckon with both the enabling and the obliterative tendencies of cosmic evolution. If the documentary's voice has a moral, it is this: deep time is generous in opportunities and parsimonious in memory. The universe can make astonishing things, but it is not obliged to let those things linger. To search the stratigraphic record of a planet like Earth for hints of distant intelligences is, therefore, to commit both to forensic patience and to a humility before the power of geological and astrophysical revision. The first stars lit the cosmic stage, but their light also showed how easily the stage can be rearranged. What does it mean to build a sky-sized city from fragments of night? That question hangs like a verdict over the beginning of the Milky Way, a proposition that a great, ordered structure could emerge not from a single architect, but from countless small, chaotic acts. The image is paradoxical and oddly intimate, a vast metropolis assembled by anonymous hands, its streets written by gravity and its architecture sketched by chance. Around 13.6 billion years ago, in the long aftermath of the cosmic dawn, that strange construction began. It began not with a single grand design, but with a swarm of star clusters and dark matter clumps twisting together, merging, and settling into a shape that would, billions of years later, cradle the sun and a small blue world. The narrator's voice in this part of the story holds two registers at once, explanatory and contemplative. On the one hand, there is a physics to narrate, the interplay of dark matter halos, tidal torques imparting spin, gas cooling and fragmenting into stars. On the other is a human scale feeling, the sense that immense, slow processes can be understood as a kind of patient workmanship. Both are necessary. The poetic framing keeps attention, the physical detail gives the spectacle coherence. The scaffolding came first. The universe's invisible backbone dark matter had already grown a web of halos, small knots in a cosmic net where gravity's pull was slightly stronger. Into those wells, ordinary baryonic gas streamed along filaments, shedding energy by radiation and beginning the hard work of condensation. In each halo, gas cooled and formed the first generations of stars. Those early star clusters were dense and vigorous, compact, metal-poor, and prone to quick, brilliant lifetimes. They were the building blocks. Rather than a smooth, simultaneous collapse of a single proto-galaxy, the Milky Way seed was an accretion of many such building blocks, each carrying its own small history, its own pattern of star formation, its own chemical fingerprint. One can imagine these proto-galactic fragments as weather systems on a planetary scale, currents crossing, colliding, merging. As they collided, they did not simply blend. Tides tore stars and gas into streams, angular momentum was exchanged, redistributed, sometimes amplified. The twisting and torquing of these fragments is crucial. Small asymmetries and gravitational nudges imparted spin to the growing system. Conservation of angular momentum forced falling gas to flatten into a rotating structure. Over time, a diffuse halo of old stars and globular clusters gathered, an extended, roughly spherical component that recorded the earliest collisions. Closer to the center, where gas could efficiently radiate and settle, denser, disk-like structures began to form. This differentiation, an extended halo and an increasingly ordered disk, was not instantaneous. It was the result of hundreds of millions of years of hierarchical assembly. The chemical signatures preserved in these first stars are a kind of paleography. Halo stars, especially the most ancient among them, carry extremely low metallicities, scant traces of elements heavier than helium. They are time capsules, their atmospheres written in an alphabet forged by the first supernovae. These abundance patterns tell a story of rapid, early enrichment by massive stars, followed by a slower, layered chemical evolution, as Type Ia supernovae added iron peak elements on later timescales. Where the halo preserves a childhood record, the disk becomes the chronicle of adolescence and maturity, more metal-rich populations, smaller star-forming clouds, and a gentler regime where planetary systems could later form. There was drama in those first mergers. Some fragments were violent and disruptive, tearing apart protodisks and scattering stars into eccentric orbits. Others arrived gently, feeding gas into the central regions and allowing a disk to rebuild, calmer and thinner each time. This patchwork of violence and calm left an imprint still visible today, a thick disk of stars, kinematically hotter, higher above the plane, made of older, more robustly enriched populations, and a thinner, rotationally colder disk composed of younger stellar cohorts. Between these components, and threaded through both, are streams and shells, the fossilized arcs of satellite galaxies and clusters that were torn apart. Modern surveys, with their mapping of motions and chemical fingerprints, operate like archaeologists reading the sedimentary layers of a city that never stopped being rebuilt. Central to the formation narrative was also the seed of a great power, the early growth of a central black hole. Amid the stirred gas and recurrent infall, conditions sometimes allowed for the formation of massive, collapsing objects, either from direct collapse in dense metal-poor regions or via runaway mergers in compact stellar clusters. These seeds, small at first, accreted gas and merged with others over time, growing into the supermassive black hole that today lurks in the galaxy's heart. Its growth was neither inevitable nor gentle. In phases where accretion was furious, the black hole may have shone as a luminous quasar, its energetic outflows shaping the surrounding gas, regulating star formation, and occasionally purging the nucleus of fuel. The presence of such a central engine is part of the Milky Way's biography, a counterpoint to the stately formation of the disk, a reminder that formation often walks hand in hand with feedback and regulation. Feedback, stellar winds, supernova blasts, and radiation pressure acted as a sculptor of sorts. Stars blow off material, massive ones explode, injecting momentum and heat into the interstellar medium. The effect is twofold. At small scales, feedback can halt local star formation by heating and dispersing gas. At larger scales, it helps to redistribute metals, enriching the gas that will form the next generation of stars. It can also create cavities and shells, pockets where second-generation stars are triggered by the compression of swept-up material. Viewed from a human perspective, this is the galaxy's way of keeping balance. Too much star formation too fast burns through gas and dims future possibilities. Too little, and the galaxy remains a dim assemblage of old relics. The early Milky Way learned a steady rhythm through trial and consequence, in which bursts of creation were followed by pauses of recovery. The Milky Way's assembly was not a solitary event, it was an interaction with a population of satellites. Many of the small galaxies and clusters that merged into the growing galaxy left behind signatures that could persist for billions of years. Some were entirely dissolved, their stars strewn into the halo. Others survived, scarred but coherent. A population of dwarf satellites that today orbit the galactic halo, bearing within them stories of tidal stripping, star formation quenching, and chemical isolation. The ongoing accretion of these satellites continues even now, a testament to the galaxy's long-lived appetite. Streams of stars arcing across the sky are visible to anyone who reads the motions. They mark former pathways of swallowed systems and demonstrate that the Milky Way remains a dynamic, evolving structure. The narrative tone here is both meticulous and elegiac. The narrator pauses to point out that the Milky Way's early epoch was also a period of harsh environments. High rates of star formation meant frequent supernovae and intense ultraviolet radiation fields. In the inner regions, collision rates and energetic feedback may have sterilized nascent planetary surfaces or stripped young atmospheres. The possibility of long-lived, stable habitats was limited by the environment's volatility. Conversely, the outer halo and the more sedate outskirts of forming disks may have offered quieter neighborhoods earlier, pockets where gases could cool slowly and where lower energy radiation environments allowed more prolonged stability. This asymmetry in space and time, where some regions mature into calm habitability sooner than others, has implications for speculative questions about ancient life. Timing matters, as does location. By the time the galaxy began to settle into a more ordered architecture, the sun's own story had not yet begun. The solar system would eventually form in a later, relatively tranquil epoch when metallicity levels were higher and the local environment quieter, conditions partly set by the processes outlined here. The Milky Way's early mergers and enrichment had, effectively, prepared the table. The heavier elements synthesized in ancient supernovae would become the raw materials for rocky planets. Yet there is an enduring tension in the story. The same forces that build also erase. Tectonic and dynamical mixing, radiation bursts, and subsequent mergers all conspire to wipe clean many potential traces of primordial activity. If, in some distant corner of the early Milky Way, complex chemistry or even technological activity left signatures, the likelihood of their survival across billions of years depends on scale and depth. Monuments left on planetary surfaces are ephemeral on geological timescales. Isotopic anomalies trapped deep in planetary mantles are more durable but harder to interpret uniquely. The galaxy's turbulent youth was both a forge and an eraser. The narrator draws closer to the observational evidence, grounding the story in measurable detail. Surveys of stellar motions and metallicities, progressively refined by missions that map positions and velocities of millions of stars, reveal coherent structures that match the merger picture. Ancient, metal-poor stars are found in extended halos and in globular clusters that survive as dense spherical relics. The thick disks, older stars show enhanced abundances of alpha process elements, consistent with enrichment dominated by massive stars on short timescales. The gradients of metallicity across the disk, the presence of kinematically distinct streams, the existence of satellite remnants, all these are the empirical signatures of an assembly history written in starlight and stellar orbits. There is also a cinematic element to the narrative. The Milky Way's emergence can be visualized as a sequence of collisions and reconciliations, of star clusters coalescing like neighborhoods that merge into a city, their roads gradually aligning into coherent avenues. The cosmic web fed steady rivers of gas into the growing galaxy, while smaller satellites kept arriving like barges loaded with fresh material and new histories. The result was neither a static object nor a chaotic stew, but a dynamic city with layers, some older, some newer, each telling a different chapter of the same chronicle. Toward the end of this chapter, the voice turns reflective. The seed that formed the Milky Way, those early star clusters that linked and twisted into larger structures, is both a physical fact and an evocative metaphor. It suggests an origin rooted in multiplicity and contingency, that grand things arise from many small, contingent processes strung together by persistent laws. For humans listening across deep time, there is a humbling lesson. The galaxy that now appears familiar, whose spirals and dimensions are measured and mapped, was once an unruly neighborhood. Its order is recent and fragile on cosmological scales. Understanding their history does not merely satisfy curiosity, it provides a context for questions about preservation, forensics, and the rarity of durable signals. Finally, the narrator makes the pivot to what follows. The Milky Way's formation set the stage for planetary chemistry, for the emergence of stable star systems, and for a long-term cosmic ecology in which life could plausibly arise. It also established a dynamical and radiative environment that would influence the survival of any traces those potential lives might leave. The next movement in the documentary will step from the galactic scale down to the intimate geology of a single planet, the Earth, examining how this vast, communal galactic history filters into a particular biography and what it means for the possibility of civilizations lost to time. The story of the Milky Way is simultaneously grand and proximate. Grand in the scale of matter and time, proximate because it is the parent environment of everything the narrator seeks to interrogate. In that ambivalence lies the continuing tension that will drive the investigation forward between what the cosmos can make and what it allows to be remembered. What does it mean for a galaxy to have a heart? The question is not literal, in the way a biologist might ask about tissue or circulation. It is a conceptual hinge. At the center of many galaxies, including the one that will cradle a small blue planet billions of years later, an object of peculiar gravity gathers mass, light, and consequence. It is a locus where time and energy concentrate, a place where creation and destruction braid so tightly that they become indistinguishable. To follow the emergence of that heart is to trace 1,000 subtle trades between motion and inertia, chance and inevitability. Billions of years after the first stars ignited and the cosmic web stitched itself into filaments and nodes, a large swath of matter, dark, baryonic, turbulent, found itself collapsing under its own gravity. The region was not special in intention, it was slightly privileged in imbalance, a fluctuation a little denser, torque a little stronger, a filamentary influx that did not abate. Under gravity's slow arbitration, angular momentum redistributed, streams of gas lost kinetic energy through shocks and radiation, and matter spiraled inward. Over a span of hundreds of millions of years, the collapse proceeded from diffuse cloud to compact structure. The spiral galaxy began to take shape, its disk brewing in the angular motion of inflowing gas, its halo studded with the fossilized remnants of earlier mergers. At the very center of that growing mass, conditions became extreme enough to give birth to something that would anchor the entire system, a supermassive black hole. There are several plausible ways such a leviathan might begin. One route is the death of the earliest massive stars. When some of the first generation of Titanic population 3 stars reached their end, their cores collapsed into black holes, seeds that, given time and access to fresh gas, could accrete and merge into larger and larger objects. Another path requires a gas cloud so dense and pristine that it collapses almost directly, avoiding fragmentation into many stars and instead plunging inward to form a massive object that then collapses into a black hole. Yet another possibility is a runaway sequence within a crowded stellar cluster, where repeated collisions and mergers build an increasingly massive object that tips over into relativistic collapse. Each pathway is less a recipe than a set of probabilities, an ensemble of ways that gravity, cooling physics, and the environment conspire. The first moments of a nascent central black hole are dramatic in the language of physics, but they are measured in processes rather than in visible spectacle. Gas that falls into the emerging potential well does not plunge straight into oblivion. Instead, it forms a disk, an accretion flow. Where angular momentum is shed, turbulence is born, and frictional stresses heat the material to extraordinary temperatures. Magnetic fields twist and break. Microscopic instabilities, such as the magnetorotational instability, act like microscopic engines, tapping orbital energy and turning it into heat. The innermost region becomes a luminous furnace. A black hole growing at high rates can radiate with ferocity, outshining entire galaxies. In those youthful epochs, the central object does not merely sit unseen, it announces its presence across cosmic distances as an active galactic nucleus, a quasar. This luminous adolescence has consequences that ripple through the forming galaxy. Radiation pressure and mechanical outflows, winds driven from the accretion disk and jets launched along the black hole's rotational axis, carry energy outward. They sweep through the interstellar medium, heating gas and driving it away from the central regions. Star formation, which depends on the quiet availability of cooled, dense gas, can be throttled or even quenched. In other places, shock fronts and compressed shells can trigger bursts of starbirth as compressed pockets fragment. The black hole's growth thus becomes an act of regulation. It feeds on gas, but in feeding it can limit the supply available for forming stars, sculpting the galaxy's evolution. From a human angle, that duality of nurturer and destroyer is emotionally complex. The center's rage is not malevolence, it is mechanistic consequence. Yet the effect is intimate in scale and long in consequence. The mass of the central black hole correlates with the stellar velocity dispersion of the bulge, an empirical relation suggesting a coordinated growth between the black hole and its stellar environment. The M-sigmat relation reads like a ledger. As the central mass grows, so too does the bulge's dynamical signature. It hints at a history of conversation between the heart and the rest of the body, a feedback loop written in motions and metallicities rather than in letters. The physical instruments of that conversation are the luminous episodes and the mechanical jets. When accretion proceeds at near Eddington rates, where radiation pressure balances gravitational pull, the central engine becomes extraordinarily bright. Photons stream outward, ionizing gas and carving out an ionized region around the nucleus. Radiation-driven winds accelerate along the disk, sometimes attaining velocities of thousands of kilometers per second. At the polar axis, magnetic collimation can launch relativistic jets, narrow beams that pierce the circumgalactic medium and inflate radiolobes on scales that dwarf the host galaxy. These jets are not cosmetic. They inject mechanical energy into the halo, heating gas reservoirs and preventing them from cooling and raining back onto the disk. The presence of jets can transform a gas-rich, star-forming galaxy into a quiescent one over relatively brief cosmic intervals. Yet another layer of consequence is chemical. When the black hole's outflows sweep through star-forming regions, they do not merely displace gas, they carry metals and newly synthesized material outward, redistributing the products of stellar nucleosynthesis. Supernovae and active nuclei together stir the galactic pot, flattening metallicity gradients and seeding the circumgalactic medium. Over billions of years, such processes help determine where and when planets with rocky compositions can arise by influencing the local availability of heavy elements. The heart's influence is therefore both dynamical and chemical. It shapes the architecture of star formation and the inventory of materials from which planets and, conceivably, life can emerge. There is an irony embedded in this dynamic. On the scales where civilizations might arise and build durable things, on the quiet outskirts of a disk, in a stable orbit around a middling star, the black hole's presence is at once remote and determinative. Remote because the gravitational reach of a central supermassive object falls off steeply with distance, determinative because the black hole helps set the pace of the galaxy's star formation history and its chemical enrichment. In that sense, a black hole is an invisible foreman who never speaks but shapes the availability of resources and the cadence of opportunities. The nuclear region itself becomes a theater of extreme phenomena. Stars that wander too close suffer tidal disruption, pulled apart in a bright flare as their matter spirals into the abyss. Dense star clusters, episode by episode, migrate inward, their dynamics altered by the black hole's gravity. Some stars are flung outward at hypervelocities, becoming lonely wanderers in intergalactic space. The central zone is a crucible of compact objects, stellar mass black holes, neutron stars, some captured and driven into a spiral, emitting gravitational waves as they near the horizon. These ripples in space-time, minute though they are by the time they traverse the cosmos, carry information about the mass and spin of the central object and about the violent dances that birth them. Observationally, the tale of a central black hole is recorded in many channels. Quasars light up the early universe. Their abundance at high redshift indicates that massive black holes had to be in place. Surprisingly early for some objects, X-ray emission maps the hot inner flows. Broad and narrow emission lines and spectra betray the velocity fields of gas at different radii. Mazes around some galaxies allow the direct measurement of central masses via precise mapping of rotation. In recent years, gravitational wave observatories have begun to add another voice. The coalescence of black holes produces space-time whispers that, when decoded, can tell the story of mergers and growth histories. Each observational modality is like a different fingerprint, and together they allow reconstruction of a complex biography. That biography is not smooth. Growth is episodic and often violent. Major mergers, collisions with other galaxies, can drive massive inflows of gas into the nucleus, triggering luminous quasar phases and rapid black hole growth. In quieter interludes, accretion is sporadic, starved by a lack of readily available fuel. There are periods of dormancy, where the central object exists mostly as a gravitational anchor, its radiance negligible, its mechanical output minimal. The modern understanding of our galaxy suggests such cycles. The Milky Way's central black hole, Sagittarius, is presently quiescent compared to an active quasar, but archaeological traces, faint X-ray echoes in the Fermi bubbles hint at past episodes of enhanced activity within the last several million years. Even a dormant heart can remember its past and the structures it has formed and the motions it imposes. For any reflection on deep time and erased civilizations, the center of a galaxy presents a double lesson. First, black holes are robust record keepers in their own way. They retain memory as mass and spin, as traces of past accretion in surrounding stellar populations, and as signatures in the circumgalactic medium. These are durable, macroscopic imprints that persist even when surface artifacts on planets are erased by geological processes. Second, the nucleation of a black hole's influence emphasizes how fragile local records can be. The most persistent archaeological traces on a planet, deeply buried isotopic anomalies, signatures embedded in rocks less subject to recycling, are not the kinds of things easily altered by distant galactic events. But the availability of the raw materials that allow such traces to exist, metals, stable planetary environments, was in part shaped by the black hole's formative influence. The emotional contour of the narrative tightens at this intersection of scale and consequence. There is awe at the scope. The mind registers the improbability that, from initial quantum jitters in the slow gathering of matter, a single compact object could come to influence the evolution of a structure tens of thousands of light years across. There is also a sobering humility. The processes that make possible life and artifacts are indifferent, often brutal, and their records fragile. Thinking about a heart that can both nurture and sterilize invites a complex feeling, respect for the elegance of physical law, and a recognition of the precariousness of any history written in ephemeral crusts of rock. The center's narrative also carries unanswered questions that hang like promises. How did the earliest, most massive black holes grow so quickly? What relative roles did direct collapse, early stellar remnants, and dense stellar dynamics play? How exactly do jets and winds couple to surrounding gas across scales from parsecs to kiloparsecs? Each unknown is not merely academic. It colors a picture of how galaxies evolve, how environments for planets are established, and how the deep time archive is written and rewritten. At the same time, the heart leaves a kind of legible trace in the galaxy's anatomy. Kinematically hot stellar populations, chemical gradients, the distribution of globular clusters, and the presence of gaseous outflows all provide ways to read past central activity. They do not, however, yield direct evidence of local cultural artifacts. The center is an editor of possibility, not a chronicler of particular human-like events. When the narrator invites the listener to imagine the past, whether to consider vanished civilizations or to reconstruct cosmic history, it must insist on a mode of probabilistic reasoning. The presence, mass, and activity cycle of a central black hole shape the likelihood of certain planetary histories, but they do not, by their nature, reveal the specific existence of intelligence. As the spiral galaxy matured, the center symphony of growth and feedback receded into a longer, quieter history punctuated by brief, violent solos. Over billions of years, the galaxy would continue to merge, to accrete fresh gas, to form stars in bursts and lulls. The central black hole would record each episode in its mass and spin, in the arrangement of stars and gas around it, and in the marks of high-energy radiation left on surrounding clouds. For the small world that would later become Earth, that record would be background, a distant, shaping motif rather than a local script. Yet the motif mattered. The elements necessary for rocky planets had been forged in earlier stellar generations, distributed and mixed by the same dynamic processes that often intertwined with central activity. The heart of the galaxy's center is thus both a physical fact and a metaphor for the tension between what is created and what is preserved. It is an engine that can ignite and extinguish, that can sculpt matter and set the conditions for habitability across the galactic disk. It is a reminder that in the narrative of cosmic history, power is not only measured in luminosity but in influence. How a compact, invisible object can harmonize the fate of billions of stars and, by extension, the chances that some small planet might carry the memory of its own brief technologies into the distant future. The story of the supermassive black hole closes not with an answer, but with an orientation. It invites listeners to appreciate the depth of physical causation and the fragility of time's archives. It positions the subsequent inquiry. Having understood how a galaxy's heart forms and exerts its will, how does that knowledge filter down to a single planetary biography? The next movement will descend from the gravitational metropolis to the intimate geology of a world, where the long hands of stellar and galactic evolution terminate in rocks, oceans, and the brief eruptions of life. There, the question becomes more pointed. What traces can survive? And how does the heart's distant pulse alter the ledger of what can be remembered? What choreography can a single point dictate across a city of billions? It is a question that compresses awe and curiosity into a single image, an almost invisible heart, whose mass is concentrated into a place no light escapes, yet whose influence organizes the motion of stars spread across tens of thousands of light years. In the Milky Way, that point exists, Sagittarius AC, and its presence turns a diffuse congregation of matter into a structured, moving architecture. The story that follows is not about drama in a human sense. It is an account of gravitational bookkeeping, collective motion, and the slow music of orbits. It is also a meditation on how the small can command the large, and how the actions of a single engine can shape the memory of a galaxy. Sagittarius AC is, in human terms, surprisingly modest, some 4 million times the mass of the Sun, confined within a region smaller than our solar system. Yet in gravitational terms, it is decisive. Within a few parsecs of this compact mass, its gravity dominates the motions of stars. Their orbits become, to first order, Keplerian ellipses, clean, predictable, and evocative of the classical mechanics that once described planetary motion. Close in, stars whirl on timescales of years and decades. Further out, orbital periods lengthen into millennia and beyond. This nested hierarchy of timescales is the first note in the galaxy's dance. Near the center, a fast, urgent tempo at larger radii. A slow, stately waltz shaped by the combined mass of stars, gas, and dark matter. But the black hole's role is both local and mediated. Its immediate gravitational sphere of influence, where the point mass approximation holds, creates a family of orbits that serve as laboratories for relativistic physics. Here, precession of periapsis, gravitational redshift, and, in principle, frame-dragging playout. Astronomers read these motions like scores, extracting the black hole's mass and spin from the subtleties of stellar paths. The inner stars become storytellers. Their eccentricities and inclinations preserve the record of past interactions, of close encounters, and of the exchange of angular momentum. Their trajectories tell not only of a central engine, but of the dynamical population that surrounds it, of binaries broken and of mass scattered. That sphere, the narrative changes. The galaxy itself behaves, less like a system of independent orbits and more like a fluid, an extended, self-gravitating medium whose collective modes dominate. Bars, spiral arms, and warps are not mere visual features. They are manifestations of resonant dynamics. A spiral density wave travels through the stellar and gaseous disk, a pattern that rotates at its own speed, shepherding stars and gas into regions of compression and rarefaction. Lindblad resonances and corrotation radii define where stars respond coherently to these patterns. where they are nudged into new orbits or trapped into longer-lived configurations. The central black hole enters this larger ballet indirectly by contributing to the deepening of the potential well, by interacting with gas flows that feed it, and by episodically returning energy to its surroundings through feedback. Feedback is the engine's second voice. When accretion onto Sagittarius Acus is vigorous, when gas reaches the nuclear region and forms a luminous accretion disk, the black hole becomes a source of radiation and mechanical outflow. Jets and winds can blast into the interstellar medium, creating bubbles, shocks, and long-lived structures like the Fermi bubbles that extend tens of thousands of light years above and below the galactic plane. Those outflows are not mere spectacle. They redistribute energy and momentum, heat gas, and can throttle star formation by depriving the disk of cool, collapsing material. In this way, the black hole acts as thermostat and sculptor. Too much feeding can quench the surrounding nurseries. Too little allows gas to accumulate and form stars again. Over cosmic time, these cycles shape the galaxy's star formation history and its chemical maturation. Angular momentum is the currency of this dance. For a parcel of gas to fall from the outer disk into the nuclear region, it must shed angular momentum. Spiral arms and bars serve as conduits for this transfer, exerting torques that drive gas inward along lanes of dust and star formation. At the same time, satellite mergers and tidal interactions can deliver fresh angular momentum and gas, reorienting the inner disk and triggering bursts of central activity. The black hole, by accreting matter, is the endpoint of one such angular momentum pathway. Its growth reflects the success of these transport mechanisms, and its episodic outbursts reflect the intermittent nature of the supply. The galaxy's stars perform a more subtle choreography, one that narrates the Milky Way's assembly. Kinematic structure streams, shells, and warped components, records past mergers. When a dwarf galaxy ventures too close and is torn apart, its stars are strewn along coherent paths. Those stellar streams arc across the sky as fossil fingerprints. They are the long, elegant swirls left by collisions long past. Chemical tagging measuring elemental abundances in stars adds another layer. Stars born in the same cloud inherit a shared chemical signature. When those stars are later scattered across the disk or halo, their composition serves as a label that ties them to a common origin. Together, motion and chemistry form a forensic toolkit. By reading the orbits and abundances of stars, one reconstructs the sequence of accretion, of mergers, of quiet growth. Yet the dance is not merely a record. It is a process that affects habitability and preservation. The central engine's influence on the distribution of metals, elements forged in stellar furnaces and dispersed by supernovae helps determine where rocky planets can form and when. Regions that experienced early, intense star formation become enriched quickly, enabling the chemistry of rocky bodies sooner than places that remain metal-poor. Conversely, the very forces that produce metals, violent starbursts, and galactic collisions can sterilize environments, strip atmospheres, and disrupt protoplanetary disks. For those pondering the possibility of ancient civilizations, this imposes a dual lesson. The black hole and the galaxy's dynamical machinery supply the raw materials for planets, yet they also enact processes that can erase fragile surface records. Tidal dynamics close to the galactic center present an extreme case. Stars and gas clouds that pass within a critical radius can be torn apart by tidal forces. Compact objects can be flung into new trajectories at high velocity. Tidal disruption events briefly illuminate the nucleus as stellar material is shredded and accreted, producing flares that are both diagnostic and destructive. These events are reminders that proximity to the heart of a galaxy means exposure to forces that do not preserve gentle histories. Over deep time, a planet too near the center would be a hazardous place, subject to frequent radiation episodes, shock waves from nearby supernovae, and the stirrings of stellar encounters that perturb orbital stability. The galactic dance writes ecological geography. Inner regions are dynamic and often violent. Middle regions are moderated by rotational support and resonant patterns, and outer regions are quieter, retaining older memories. The interplay of collective modes, bars, spirals, warps, and central influence produces a rich catalog of timescales. Orbit near Sagittarius. Circling years or decades, stars at the sun's radius, orbit on a few 100 million-year clock. The bar may rotate with a pattern speed on the order of tens of millions of years. These layered tempos overlap, interacting through resonant couplings. When resonances line up, they can produce long-lived structures. When they misalign, they seed chaos. Over billions of years, these interactions can thicken disks, warp planes, and redistribute angular momentum in ways that are both deterministic under gravity and sensitive to initial conditions. The result is a galaxy that is predictably unpredictable. Its larger scale form is governed by well understood physics, yet the details of its structure record a contingent history. Observationally, the choreography is read with instruments that translate motion into data. Radio interferometry traces the flaring, compact emission of the nucleus. Infrared and optical astrometry follow the orbits of nuclear stars with exquisite precision. X-ray telescopes detect accretion and tidal disruptions, and gamma-ray observatories map larger-scale energetic outflows. In recent years, gravitational waves have opened a new doorway, promising to hear the merging footsteps of black holes and compact objects. Each modality is a different sense organ for the galaxy's movement, a set of ears and fingers with which to feel the rhythm. Together, they allow reconstruction of both the slow sweep of secular evolution and the sudden exclamation points of episodic activity. There is a moral cadence to all this. The galaxy's dance is an exercise in payoffs and penalties. The processes that build, accretion, star formation, mergers also create conditions for erasure, feedback, shocks, tidal stripping. The black hole embodies this dialectic. It is at once the engine that can concentrate mass and the mechanism that can disperse energy so violently that nascent structures are unmade. For those who imagine searching for ancient traces across deep time, the implication is stark. Durable records must contend not only with the planet's geology and atmosphere, but with the galactic choreography that shaped the environment long before any intelligent observer could arise. The black hole also encodes memory in a durable, if abstract way. Its mass, spin, and the distribution of surrounding stellar orbits preserve a history of accretion and mergers that is less susceptible to local geological erasure. Whereas a stone monument on a planet's surface can be worn away by weather, the integrated dynamical state of a galaxy resists such local editing. In this sense, the center's archive is coarse but robust. It records episodes of growth and disturbance in ways that are legible across cosmological times. The traces it leaves, metallicity gradients, kinematic heating, central mass concentration, are the largest scale fossil record of a galaxy's formative epochs. If the dance of the stars is a music of gravity, then the listener is left with two feelings: smallness and intimate connection. Smallness, because a single compact engine can govern motions across unimaginable distances, reducing human time to a flicker in a slow, majestic choreography. Intimate connection, because the same laws that allow stars to orbit a black hole also allow atoms to bind, planets to form, and life to arise. The same physics that writes grand motion also allows fragile memory. The narrative tightens here. To read the galaxy's dances, to learn both the conditions of possibility and the conditions of erasure. It is to understand why some regions could nurture long-lived habitats and why others could not, why some histories persist in stellar motions and why others are swallowed by the tides of time. As the account of the Milky Way's choreography slows into a pause, it becomes clear that the central engine is neither villain nor savior, but a participant in an indifferent system. Its power is instrumental. Its consequences are the arithmetic of gravity and thermodynamics. The next movement of the story will trace that instrumentality down to a single planetary surface, how the galaxy's rhythms are translated into the chemistry and geology of a place called Earth, and how those processes set the stage for fleeting agents capable of asking the very question with which this chapter began. The audience is invited to lean forward, for the dance continues, and the choreography of stars and black hole ultimately filters into rock, water, and the fragile artifacts that might, or might not, survive the unrelenting passage of deep time. What does it mean for a single star and its attendant planets to come into being inside a galaxy that has been busy for billions of years? The emergence of System M is at once an answer to that question, and a new set of questions folded into it. It is a local story that inherits the entire previous history of the cosmos, the seeded metals from ancient supernovae, the dynamics of the galactic disk. The slow recycling of gas then compresses those grand processes into a small, violent laboratory, a rotating disk of dust and gas that will forge rocky worlds, volatile envelopes, and the complex chemistry on which life and, perhaps, culture depend. To understand System M is to follow a chain of contingent events. The stars of the Milky Way had already run through several generations of nuclear forges. Those early furnaces had sown the interstellar medium with oxygen, carbon, silicon, iron, the elements necessary for rocky planets. The region where System M would form was not special by decree. It was simply a parcel of the galactic disk whose metallicity and dynamical history made it suitable for building small, solid worlds. That suitability is a subtle kind of privilege, enough heavy elements to make rocks and plates. Not so violent an environment that nascent disks are shredded by radiation or frequent close encounters. This balance and narrow window carved by the galaxy's own tumult sets the first constraint on possibility. The protoplanetary disk that birthed System M was a thin, ephemeral thing when compared to cosmic scales. Within a few million years, the gas that had fed the young star would either accrete onto the star, be driven away by stellar winds, or be locked into nascent planets. But within that brevity, the disk was a riot of motion and chemistry. Dust grains collided and stuck, forming ever larger aggregates. Pebbles concentrated in pressure traps and streamed inward. Planetesimals, gravitationally bound rocks the size of towns, accreted further, their collisions energetic enough to melt and differentiate their interiors. It is useful to picture this stage as a kind of centrifugal kitchen. The central star is the stove, the disk is the simmering pan, turbulence, drag, and local pressure maxima are the utensils. Where cooling is efficient, dust-rich regions fragment and give rise to rocky embryos. Where pebble flux is high, cores can grow rapidly and, if they reach a critical mass before the gas dissipates, capture thick envelopes of hydrogen and helium. The location of the snow line, the radius in the disk where water ice can persist, acts as a chemical delimiter. Inside it, rocky worlds assemble from refractory materials. Outside it, volatile rich bodies grow, capable of becoming gas giants or icy worlds. The architecture of System M, the number, size, and composition of planets, was determined by these early spatial distinctions and by the timing and frequency of major collisions. One of the most consequential events in any terrestrial planet's early life is the sequence of giant impacts. These are not rare footnotes, but an integral phase in the consolidation of mass. When protoplanetary embryos collide, they do not gently settle. They slam with energy sufficient to melt surfaces, vaporize volatile envelopes, and even launch material into orbit. One such catastrophic collision can create moons, strip atmospheres, or obliterate any early surface record. In the narrative of System M, such episodes shaped the planet's spin, its axial tilt, and its inventory of volatile compounds. The cup from which oceans would later be poured was contoured in molten sprays and vapor plumes. The chemistry of volatiles, water, carbon-bearing molecules, nitrogen, arrives by two main deliveries. Some is inherited locally from the disk's inner reservoirs. More often, a substantial fraction rides inward on icy planetesimals and comets from beyond the snow line. A late-stage bombardment, composed of leftover planetesimals and bodies scattered inward by giant planet migration, can seed a young terrestrial world with the molecules necessary for oceans and prebiotic chemistry. But those same impacts are erasers as well as suppliers. They obliterate nascent crustal fabrics, reset isotopic clocks, and bury or expel any fragile arrangements that might have briefly existed at a surface. Beneath the surface, differentiation transforms chaos into order. Heat from accretional energy, short-lived radionuclides, and subsequent impacts melts the young planet internally. Denser materials sink to form an iron-rich core. Lighter silicates buoy upward to create a primitive mantle and crust. This segregation is not merely structural, it unlocks geochemical pathways. The metallic core can host a convecting dynamo, the moving conductive fluid that generates a magnetic field. That field, when sustained, becomes a planetary shield. It diverts energetic particles from the star, protects an atmosphere from sputtering by the solar wind, and stabilizes surface conditions enough to allow a long-duration experiment called habitability. The presence of a magnetic field depends on a precarious set of conditions: the rate of cooling of the core, the presence of light elements that facilitate convection, and the planet's rotation. If the core solidifies too early, the dynamo can die. If the star is violently active in its youth, the protective envelope must be thick enough to survive early stripping. For System M, the interplay of core formation and stellar temperament set yet another constraint on the planet's future, one that would echo across billions of years. Atmospheric composition is an equally delicate ledger. Initially, the atmosphere may be a dense, steam-heavy mantle produced by outgassing from a molten surface and by impact volatilization. Over time, photochemistry driven by stellar ultraviolet radiation and subsequent biological activity can radically change the atmospheric mix. Carbon dioxide, nitrogen, methane, and later oxygen trace the history of geochemistry and life's interventions. The early greenhouse conditions, regulated by the carbonate-silicate cycle, can prolong surface liquid water despite a faint young star. Conversely, runaway greenhouse or atmospheric erosion can sterilize a planet. On System M, these chemical pathways were negotiated in the first 100 million to billion years, as continents began to rift and coalesce and oceans pooled in basins. Surface geology, the slow apparatus of plates, mountains, and oceans, begins to carve the planet into diverse environments. Plate tectonics, if it emerges, is at once an engine for chemical recycling and a catalyst for preservation. Subduction recycles crust into the mantle, erasing surface inscriptions, yet it also builds continental crust that can resist erosion and shelter deeply buried records and cratons. The carbonate silicate thermostat stabilizes climate over geologic timescales, while mountain building exposes fresh rock to chemical weathering, drawing down CO2. It is within this geodynamic interplay that windows of environmental stability can open, long enough for life to take hold and, in speculative scenarios, for intelligence to arise. If life appears, its own processes begin to write into the stratigraphic archive. Microbial mats trap sediments, stromatolites build layered structures, and metabolic byproducts alter atmospheric chemistry. The great oxidation event, an oxygenation of the atmosphere produced by photosynthetic organisms, transform both chemistry and preservation potential. Oxygen both facilitates the formation of oxidized minerals that are stable for eons and accelerates the breakdown of reduced organic molecules. Life's imprint is therefore ambivalent. It creates both durable markers and processes that can complicate the geochemical record. All of these stages bear directly on a central speculative question: could an intelligent, technological civilization have risen on System M long before the present? And if it did, could geological and astrophysical processes have removed its traces? This is where the forensic lens narrows from planetary formation to preservation science. The short answer is that preservation is possible, but only under stringent circumstances. Surface constructs, monuments, cities, roads are exquisitely vulnerable on timescales of millions to hundreds of millions of years. Erosion, sedimentation, chemical weathering, and tectonic reworking steadily erase topography and lithify sediments. Rivers grind basalt and granite. Winds reduce stone to sand. Oceans bury continents in thick blankets of sediment that will later be metamorphosed. Even robust materials, metals, glass, ceramics, are susceptible to chemical alteration. Over 1 billion years, the planet's crust is a dynamic, recycling skin. Anything that exists near the surface is likely to be reworked or subducted. Deep burial is the essential preservational strategy. Material that is quickly buried within resistant sedimentary contexts, lacustrine basins, anoxic marine shells, or ash layers that lithify into tuff, has a higher chance of surviving as a recognizable anomaly. Even so, tectonic metamorphism can alter mineral identities and reset isotopic systems. Some classes of evidence are more resilient. Certain isotopic anomalies, non-biological distributions of refractory synthetic elements, or the presence of long-lived radionuclide ratios unexplainable by natural nucleosynthesis. The deep mantle, shielded by stability and cratonic roots, can preserve geochemical anomalies, but interpretation is highly ambiguous and requires global context. What, then, would constitute a robust trace of a vanished intelligence? Large-scale planetary engineering projects, global-scale isotopic manipulation, anomalous enrichment of elements with no plausible natural source, or macroscopic constructions embedded deeply into stable crustal provinces would be the most unambiguous candidates. An engineered rearrangement of entire mineral layers or an isotopically fractionated global atmospheric residue could survive for a very long time. Synthetic molecules with exceptionally stable bonds, if buried and shielded from chemical destruction, might persist as rare mineral inclusions. But all of these require extraordinary scale, materials thought to be durable or deliberate embedding in geologically stable contexts. There is another set of possible signatures that are subtle but informative: anomalies in sedimentary layering, inexplicable spikes in certain rare elements, or abrupt shifts in isotopic baselines that cannot be reconciled with volcanic impact or biological processes. For example, a sudden and globally synchronous deposit rich in high-density alloys, or an abrupt enrichment in noble metals distributed in a pattern inconsistent with known meteoritic sources, would demand an explanation beyond normal geologic cycles. Yet here the burden of proof is heavy. The natural world produces many outliers, and the interpretive challenge is to exclude all plausible natural mechanisms before assigning agency. The scientific prudence of the documentary voice must be explicit. Speculation about vanished civilizations is not an invitation to myth, it is an exercise in conditional probability. The prior probability that intelligence arises and then engineers planetary-scale projects is low. The prior probability that those projects will be both constructed in such a way as to survive deep time and unambiguously distinguishable from geological processes is lower still. But the question remains interesting because it is falsifiable in principle. Careful geochemical, mineralogical, and stratigraphic studies can set upper limits on the existence of certain anomalies and can identify contexts where artificiality is a more plausible cause than natural processes. This leads to a methodological insistence. The search for ancient techno-signatures on System M or on any world cannot be a search for romance. It is an exercise in multidisciplinary archaeology, writ planetary, a convergence of high-resolution geochronology, isotope geochemistry, sedimentology, materials science, and an understanding of astrophysical forcing. It requires asking precise questions. What would an artificial signal look like after a billion years of tectonic reworking? And designing measurements sensitive enough to detect anomalies beyond natural variability. It also requires humility. Many anomalies will likely be ambiguous, and many more will eventually be explained by novel, natural processes. There is a poetic weight to this pragmatism. The same processes that make complex life possible, plate tectonics that recycle nutrients, stellar alchemy that seeds planets with heavy elements, impacts that deliver volatiles, are also the processes that erase the traces of transient agents. It is the paradox of deep time. Possibility and oblivion are braided together. System M's emergence made certain futures available. Its geology and astrophysical environment dictated how durable any record of those futures might be. The planet is generous in offering opportunities and parsimonious in the memory it keeps. For a listener attuned to scale, this is both sobering and oddly consoling. Sobering because it normalizes the fragility of human artifacts against the yawning patience of geological processes. Consoling because it reframes the human endeavor not as a quest for immortality in stone alone, but as part of a broader custodial project to extend memory through records deposited in multiple media, to place some durable inscription into the relatively stable parts of a planet's anatomy, and to understand how the planet itself archives its past. As the narrative of System M closes and the documentary voice turns to the next phase of inquiry, the focus narrows further. If System M is the stage, what are the instruments by which an ancient signal, if it existed, would be recovered? The answer will require descending from planetary formation into thick cratons, paleo-ocean basins, and deep mantle samples. It will require the patient, methodical work of searching for anomalies that resist natural explanation. The scene is set. A planet formed from fossilized starlight, shaped by catastrophic collisions and slow convection, hosting an environment that both permits and forgets. The question now is not whether System M could have borne complexity. On that point it leans toward yes, but whether the fabric of deep time allows any localized, transient achievements to leave a readable trace. The ensuing chapters will be devoted to that examination, to the forensic science of detecting faint, obscured whispers in the rock record, and to the thought experiments that separate plausible erasure from possible survival. What does a galaxy do when it is not being observed, when it goes on with its slow, indifferent labor of assembling stars, stirring gas, and spinning dark matter into shape? That thought opens the 11th act of this long story. A meditation on the Milky Way, not as a backdrop, but as an agent, a vast, non-sentient sculptor whose motions, chemistry, and violence shape the emergence, endurance, and erasure of everything smaller, planets, biospheres, perhaps even civilizations. It is a question that reframes scale, not only how the universe began, or how a star and a planet formed, but how the vast, communal life of a galaxy mediates memory across deep time. The galaxy's first duty is provision. In the metaphoric ledger of existence, the Milky Way provides raw materials, metals, volatiles, dust, that planets need to be rocky, wet, and chemically complex. That chemical provisioning is neither uniform nor continuous. It is written by a history of star formation and feedback. Early, massive stars burned and died, scattering heavy elements into the interstellar medium. Subsequent generations homogenized this enrichment unevenly. The result is a radial and temporal gradient of metallicity. Close to the galactic center and in regions that have experienced intense star formation, heavy elements are abundant. Farther out, and in pockets that have remained quiescent, the raw material remains impoverished. The Sun, and thus System M, inherited a local chemistry that was the sum of this history, a particular combination of iron, silicon, oxygen, carbon, and volatile compounds that made a habitable world possible. That inheritance was not simple providence but contingency. It depended upon the timing of nearby supernovae, on how gases mixed in the local interstellar medium, and on whether a favorable parcel of material had been shepherded into a collapsing cloud at just the right moment. Provision is also a ledger of risk. The same stellar furnaces that synthesize the periodic table also create the hazards that can. Wipe clean a world surface record, supernovae seed space with high-energy particles and shock fronts, gamma-ray bursts, rare though they are, could sterilize wide swaths of a galactic disk if directed nearby. Intense ultraviolet fields in regions of active star formation can strip atmospheres from nascent planets. The Milky Way organizes these dangers by location and epoch. Dense star-forming regions, the kind that produce clusters and massive stars, are hazardous during their youth. The inner galaxy closer to the crowded bulge, with higher rates of interactions and a deeper well of gravitational stirring, offers less durable conditions for long, uninterrupted habitability than calmer outer disk zones. There is a geography of fragility. The galaxy structure assigns likelihoods to stability and disruption. Wave patterns add a metronome to this geography. Spiral arms are not merely ornaments. They are highways of density, regions where gas is compressed and star formation is triggered. As the sun orbits the galactic center, it does not glide through a uniform medium but weaves in and out of these arms on time scales of tens to hundreds of millions of years. Each passage raises the probability of nearby supernovae and perturbations to the Oort cloud, the vast, diffuse reservoir of icy bodies that surrounds the solar system. The gravitational nudges of spiral arms and of individual massive molecular clouds within them can increment the flux of comets into the inner system. Those cometary showers behave as both creators and destroyers. They may deliver volatiles that nourish a young planet, and later rain down impacts that erase surface structures and reset geological clocks. The galaxy's rotation thus modulates planetary histories with a cosmic heartbeat. The Milky Way also shapes the flux of cosmic rays, a subtle but persistent agent of change. Cosmic rays charge particles accelerated by supernova shocks and by energetic processes, new black holes, permeate interstellar space. Their intensity varies with galactic environment and with proximity to active regions. When cosmic rays impinge upon atmospheres and surfaces, they catalyze chemistry, produce isotopic signatures, and can increase mutation rates for organisms that live near the surface. Over geologic stretches, this modulation can nudge evolutionary trajectories or alter preservation potentials. In deep time, a period of heightened cosmic ray flux might leave an isotopic or molecular fingerprint. It might also correlate with biological turnovers. The galaxy, in this sense, becomes not simply a material provider but a background architect of chemical and biological outcomes. Motion matters in another register, stellar encounters. Stars are not fixed signposts. They wander, they cluster, and they drift, carrying their own retinues of comets and planetesimals. The sun was almost certainly born in a cluster, some cohort of sibling stars that has since dispersed. That early cluster environment would have conditioned the young solar system, exposing it to close stellar flybys that truncated outer disks, exchanged comets, and perhaps even seeded material from other nascent systems. Over the course of billions of years, the solar system has experienced other close passages of stars and molecular clouds. Each meeting has the potential to perturb the Oort cloud, injecting comets inward to slightly alter planetary orbits or, in the extreme, to eject planets into interstellar space. The galaxy's population of stars thus acts as an invisible community of neighbors whose proximity can rearrange destinies. If the galaxy is a stage of influences, it also keeps a record, an imperfect distributed archive of its own making. Galactic archaeology has revealed that stellar motions and chemical abundances encode past events. Streams of stars arcing across the sky are fossilized signatures of dwarf galaxies long devoured, globular clusters preserve. Ancient compositions, gradients in metallicity and element ratios, map the cadence of star formation and the timing of enrichment. These are durable marks. They persist across billions of years because dynamical processes on galactic scales are slow and because the motions of stars record collisions that cannot be smoothed away quickly. The Milky Way's history, in that sense, is written in the motions and compositions of its stars. It is a coarse archive, one that cannot speak to the details of surface monuments on a planet, but that does chronicle the availability of material and the frequency of disruptive events. This duality, durable galactic fingerprints versus fragile planetary inscriptions, contains the core of the documentary's moral scale preserves some things and erases others. The Milky Way can preserve the time and place of enrichment events within the chemical memory of stars. It cannot, however, guarantee that a technological project built on a planet's crust will be legible after 1 billion years. The processes that govern planetary geology, subduction, metamorphism, erosion, operate on timescales and with mechanisms that are local to the planet. The galaxy's influence is more about statistical predisposition than direct archival care. It sets the stage, nudges the probability, alters the risks, but does not itself become the guardian of surface artifacts. There are, nevertheless, speculative channels by which the galaxy could assist in long-term memory. Interstellar probes, if constructed with intent, could in principle survive longer than planetary crust. A durable probe placed in a stable orbit around the galactic center or embedded in a Kuiper Belt analog might remain detectable for eons. But here the galaxy's environment is not kind. The interstellar medium, though tenuous, is abrasive over billion-year spans. Dust sputters surfaces. Micrometeoroid impacts wear away delicate features. Cosmic rays slowly damage electronics and materials. Stable orbits exist, but the galaxy's dynamical processes, passing stars, tidal influences, encounters with molecular clouds perturb them on multi-million-year timescales. Any techno-signature that claims permanence must therefore be either extraordinarily massive, buried deep within geologically stable crust, or continuously maintained, an unlikely combination if the originating civilization has vanished. The Milky Way also widens the scope of what might be sought as a signature. Rather than searching solely for surface ruins, the attentive investigator can look for astrophysical scale anomalies that a civilization might leave behind, deliberately or inadvertently. Unusual isotopic ratios in interstellar dust, anomalous distributions of metals in a local bubble, or energy patterns inconsistent with known astrophysical processes could be hints. The galaxy has been thought of as a medium in which techno-signatures might be propagated, intentionally beamed messages, engineered stellar light curves, or megastructures that modify local infrared emission. Each of these concepts is speculative and carries practical hurdles, but their value is that they are, in principle, more robust against geological erasure because they operate on scales where the galaxy's own slow dynamics are the relevant timescale. There is also the question of timing and hindsight. The sun's migration through the galactic disk, radial migrations caused by interactions with spiral arms and transient features, means that a star and its planets are not eternally fixed in one galactic neighborhood. System M's birthplace might not coincide with its current galactocentric radius. That migration complicates any attempt to reconstruct the local environment's history from present conditions. An observer interrogating Earth's past must account for the fact that elemental abundances, encounter rates, and radiation backgrounds change not only because of time but because of spatial relocation to a structured galaxy. The Milky Way's large-scale motions thus blur the mapping between local geology and galactic history. From the vantage of emotion and human perspective, these facts compress into a peculiar blend of smallness and connectedness. An individual planet is a tiny gear within the galactic machine, yet the machine's turning sets the probabilities of life's emergence and the persistence of its records. This inversion provokes humility, the idea that the entire history of a world, its chemistry, its catastrophes, its fragile cultural flourishes, can be framed as a response to distant, slow motions of a galaxy imparts both melancholy and a kind of awe. Human histories, however catastrophic in their own terms, are mere ripples on a sea whose tides were set long before the first cities were imagined. The Milky Way also offers a practical lesson for the search for vanished intelligences. Any claim of an ancient technological trace must be framed within the galaxy's ecology. What isotopic anomalies could plausibly survive the mixing of the interstellar medium? Which deposit types are least likely to be recycled on a planetary scale? Which astrophysical signatures are most resilient to false positives produced by natural processes? A rigorous search becomes a multi-use scale endeavor, combining geochemistry and sedimentology with stellar kinematics and galactic scale modeling. It means not only asking where and how artifacts might survive, but also where the galaxy had given the highest likelihood of their creation in the first place. Regions and epochs where metallicity, dynamical stability, and a benign radiation environment might have overlapped. That search yields a second emotional undertow, urgency. The galaxy's long memory favors certain classes of evidence: stellar abundances, orbital relics, circumstellar dust compositions that observers can still measure. The tape of a planet's surface record, meanwhile, continues to be rewritten by erosion and tectonics. The act of searching, therefore, is a race against slow erasure, not against sudden removal. It is patient work, governed by samples, measurements, cross-disciplinary inference. It requires humility. Most anomalies will have mundane explanations. It also requires creativity. Some traces might be subtle, encoded in isotopic offsets or in unusual mineral phases that only sensitive instruments can reveal. Finally, the Milky Way's role refracts back on the original question of origins and destiny. The galaxies where physics and contingency braid into outcomes that allow observers to ask about origins at all. It is not a benevolent parent, but an assemblage of processes that both enable and limit. That ambivalence is central to any narrative about deep time. The Milky Way made System M possible by furnishing elements in a dynamical context. It modulated the flux of deliveries and destructions. It preserved some signatures in the motions and chemistry of its stars while leaving the fine grain of planetary culture, vulnerable to geological forgetting. To stand on a small planet within such a vast machine is to live between scaffolding and erosion, privileged in that a galaxies. Long history produced the conditions for life, humble in that the galaxies' indifferent dynamics ensure that most things will be lost. If there is a closing image to carry forward, it is not one of finality, but of orientation. The Milky Way is neither witness nor judge. It is the context in which possibilities are negotiated. Its spirals trace long corridors of chance. Its bulge harbors the record of tumult. Its halo cradles the fossilized debris of collisions. For the investigator of deep time, the galaxy is both map and meter. It guides where to look and sets the tempo of expectation. Understanding the Milky Way is not an abstract cosmological indulgence. It is a necessary precondition for any patient. Forensic attempt to read the faint, eroded traces of what might once have been. The next movements of the story will press downward from the galactic metronome into the particularities of paleoproxies, isotopic oddities, and the places on Earth where deep time has preserved its secrets most faithfully. The Milky Way's role is the frame, the rocks are the photograph. To interpret one, the other must be known. What would have happened if the sun had been born somewhere else in the Milky Way? That question is less a counterfactual thought experiment than a scalpel for a deep intuition. Position matters. Not merely the planet's position around its star, but the star's position within a galaxy whose vastness is textured with danger and opportunity. The human sense of being at home beneath the steady sun rests on a stack of contingencies, astronomical, geological, chemical, that together form a narrow corridor of habitability. If the solar system's local address had been otherwise, the history of life on Earth might look unrecognizable, or it might not exist at all. The first layer of protection is galactic. The sun is not a citizen of the crowded central city of the Milky Way. It lives in a relatively quiet suburb, roughly 30,000 light-years from the galactic center, in a modest spur between major spiral arms. That location is not accidental in its consequences. Galactic centers are energetic neighborhoods, a high density of stars, more frequent close encounters, a higher rate of catastrophic events such as supernovae and the occasionally lethal gamma-ray burst. A star too near that bustle faces a bombardment of high-energy radiation and encounters that can strip atmospheres, inject sterilizing bursts of particles, or hurl cometary bodies inward. Conversely, a star too far out in the dim halo risks metal paucity. The raw materials for rocky planets, for chemistry, and for complex life may simply be lacking. The sun's position, at a moderate radius and in a low-density spur, sits between these regimes, removed from the most violent concentrations, yet within a metallicity sweet spot where heavy elements forged in earlier generations of stars are sufficiently abundant. That metallicity matters. The periodic table that composes rock, water, and biochemistry was assembled in earlier stellar generations. Carbon and oxygen, silicon and iron, phosphorus and sulfur, each of these elements is the residue of stellar life and death. The local enrichment of the interstellar medium around the proto-exolar cloud determined whether a disk of dust and gas could make terrestrial planets at all. The sun's birth environment had enough of these heavier elements to build a world with a differentiated core, with silicate crusts and a volatile budget, able to hold oceans and an atmosphere. A star born in a metal-poor pocket would likely lack the building blocks for an Earth-like planet. One born in an overly metal-rich neighborhood could have created a different planetary architecture altogether. The galaxy, through its own history of star formation and feedback, had already arranged the chemical ledger by the time System M condensed. Protection is not provided solely by distance from the center. It is also a function of orbital choreography. The Sun's orbit around the galactic center is relatively benign, nearly circular, modestly eccentric, and, crucially, it sits near what astronomers term the co-rotation zone. Spiral arms are regions of density enhancement that act like slow traffic jams in the galaxy's disk. Interstellar gas piles up. Stars are born, and supernovae follow. A star sweeping through these arms frequently encounters freshly forged massive stars and the after effects of their explosive deaths. Crossing spiral arms raises the local hazard rate. The Sun's orbit reduces the frequency and severity of these crossings. In effect, System M spends long stretches in a calmer band of the disk, avoiding the worst of the star formation melee. The result is fewer nearby supernovae over geological time and a lower integrated flux of cosmic rays, factors that influence atmospheric chemistry, mutation rates, and the preservation of fragile surface records. Closer, more intimate shields are woven within the solar system. The Sun is a remarkably stable star, a get-tight main sequence star with a predictable, steady output across billions of years. Compared with smaller, more volatile dwarfs that flare wildly, the Sun's temperament is mild. That steadiness matters. Life at a planetary surface requires a relatively stable irradiance and spectral distribution over long spans to permit sustained climates and slow biochemical evolution. The Sun's lifetime of order, 10 billion years on the main sequence, provides a generous temporal canvas for complexity to arise and deepen. If the host star were short-lived or erratically luminous, a complex biosphere would struggle to persist long enough to build and retain technological cultures. But the Sun's role is not only passive stability, it actively shapes the local interplanetary environment through its wind and magnetic sphere. The heliosphere, the bubble of charged particles inflated by the solar wind, acts as the solar system's first line of defense against galactic cosmic rays. Its size and efficacy depend on both the Sun's activity and the density of local interstellar material. A robust heliosphere reduces the flux of high-energy particles that penetrate atmospheres and alter chemistry or increase background mutation rates. The Sun's moderate motion through a rarefied local interstellar cloud and its stable wind over much of its life helped maintain a heliospheric shield that was neither too brittle nor too compact. Those conditions lowered the rate at which high-energy particles reached Earth, contributing indirectly to a more controlled evolutionary environment. Jupiter plays a decisive, ambiguous role in this protection economy. It is often lauded as the solar system's cosmic umbrella. Its massive gravity deflects, captures, rallies, and ejects countless comets and asteroids, reducing the bombardment rate of the inner planets. There is truth in that narrative. Jupiter's position and mass have shepherded many small bodies into safe orbits or ejected them into interstellar space. Yet Jupiter is also a resonant agent that can redirect objects inward. Collisions and gravitational nudges can sling comets from the distant Oort cloud into the inner system, where they become impactors. The net effect of a giant planet depends on architecture, mass, orbital eccentricity, and timing. In System M, Jupiter's configuration appears to have reduced the catastrophic impact rate sufficiently to allow long stretches of tectonic and biological continuity, while still supplying the late delivery of volatiles that probably seeded Earth's oceans. It is an instructive example of how protective features are rarely absolute. They trade one class of risk for another, and their net benefit is contingent. Even the Moon is part of the protective ensemble. Its presence, huge relative to Earth's size, stabilizes Earth's axial tilt, reducing extreme obliquity variations that could otherwise plunge the climate into chaotic swings. A steady tilt stabilizes seasonal cycles, which in turn fosters long-term ecological niches and climate-regulated evolutionary pathways. The Moon also influences tides, which create ecotonal zones of ecological richness, possibly providing crucibles for prebiotic chemistry and early life. Without it, the planet's axial dynamics might be a different, less forgiving story. Cosmic threats, however, extend beyond these comforting architectures. Supernovae within a dozen to a few dozen light-years can deplete stratospheric ozone, exposing the surface to ultraviolet sterilization and altering atmospheric chemistry. Gamma-ray bursts, although rare, can sterilize entire hemispheres if directed nearby. The passage through dense molecular clouds can compress the heliosphere, increasing cosmic ray flux and perturbing the Oort cloud, while close stellar encounters can destabilize outer reservoirs and send a deluge of comets inward. Each of these dangers is mediated by the Sun's position and the system's architecture. An earlier residence in a denser stellar birthplace, or a galactic voyage to a spiral arm at a bad time, would raise these risks dramatically. The Sun's relatively sedate neighborhood and orbital cadence reduce the integrated probability of such catastrophes during the critical windows in which life diversified on Earth. A narrative of protection might suggest design or intention, but the documentary voice here insists on humility and contingency. The solar system's position and configuration are the result of stochastic processes. The timing of nearby supernovae before the Sun's birth, the dynamics of the protostellar cluster in which the Sun formed, the accretion history that led to Jupiter's mass and orbit, the angular momentum distribution in the protoplanetary disk that produced the moon-forming impact. Each step was a probabilistic hinge. The fact that these outcomes conspired to favor a long, habitable epoch on Earth is therefore an instance of fortunate convergence, not cosmic benevolence. That convergence has consequences for memory, i.e., the same architecture that shields life from some hazards also affects the preservation of its traces. A stable orbit, moderate bombardment rates, and an atmosphere that allows sedimentation and lithification improve the odds that biological and technological signatures enter. The geological record. Yet deep time is unforgiving. Plate tectonics recycles crust, erosion and sedimentation bury and obliterate, chemical weathering dissolves artifacts. The Sun's protection is a condition for life, but not a guarantor of the permanence of its works. The galaxy and the solar system offer a window of habitability and a means to lower existential risks, but the archival of that existence into durable, unambiguous markers, robust enough to survive hundreds of millions or billions of years, depends on choices and on geologies more than on stellar favor. This is where the argument tightens into ethical and methodological urgency. If the geological record is a palimpsest, then forensic attention must be meticulous and creative. The search for ancient traces, whether for Earth's own deep past or for technosignatures elsewhere, requires a cross-scale sensitivity that ranges from isotopic anomalies in ancient zircons to the patterning of metals in shield cratons, from the distribution of rare elements in marine sediment to unusual, non-natural ratios of long-lived radionuclides. The solar system's location gave life the time and stability to write something. The planet's geology determines how legible that writing remains. The investigative task thus becomes twofold: to understand how protective cosmic and stellar factors permitted the emergence of habitability, and to understand how planetary processes have since edited, hidden, or destroyed the traces of that emergence. The conclusion to be drawn is both sobering and capacious. The Sun's modest, stabilizing light did more than warm a planet. It sat within a web of protections and hazards whose patterning in the galaxy made Earth's history possible. Position in the Milky Way, stellar temperament, giant planet architectures, and satellite dynamics together crafted a window in which complexity could flourish. Yet these same factors also mean that the survival of any artifact beyond deep time is not guaranteed. Rarity and fragility are twin lessons. The window for a civilization's rise is narrow and precious, and the likelihood of its enduring signature is low, unless particular choices or extraordinary scales of engineering were undertaken. In the last note, the voice of the documentary draws back to the larger composition, from the universe's first breath to the settling of galaxies, from the forging of elements in ancient stars to the slow choreography of the Milky Way. The Sun's role is a final local synthesis. It is the small, steady actor on a vast stage whose specific address and temperament made the conditions for life plausible. That fact should produce two responses: curiosity and caution. Curiosity, because the chain of dependencies invites inquiries across disciplines: astrophysics, geochemistry, paleoclimatology, planetary science, and archaeology. Caution, because the fragility of memory in deep time demands rigorous standards of evidence, patient methods, and an awareness that many anomalies will lead back to natural processes rather than human-like agency. If there is a moral cadence to close on, it is one of stewardship. The Earth occupies a narrow sweet spot in a galaxy of hazards. Its habitability and the faint ledger of its past are gifts of contingent cosmic histories. To search for ancient traces on this planet or any other is to accept a double responsibility: to look with scientific rigor and to act with the prudence of custodians. The sun's benign light allowed a tiny vantage point from which self-aware beings could ask about origins, about erasure, and about their place in time. That vantage confers a duty to preserve knowledge, to archive carefully, and to ensure that if humanity's own lights are to be legible in deep time, the inscriptions are placed where both planetary geology and the indifferent choreography of the galaxy are least likely to erase them. In the end, the image that lingers is a modest one, a small blue world quietly orbiting a steady star, itself gliding through a slow, indifferent galaxy. That world is both accidental and precious, an improbable confluence of place and process. The sun did not guarantee life. It did not decrete permanence. It merely offered a stable stage, a protective bubble, and a clock that ticked long enough for complexity to emerge. The rest was contingency, collisions and chemistry, stability and catastrophe, the patient work of sediment and the caprice of impacts. Understanding that confluence is the work of the story so far, an account that ends not with finality but with an invitation to look, to measure, and to keep a careful ledger of what might otherwise be forgotten beneath the slow hands of deep time. What if the word ending is merely a comma, and the universe is still mid-sentence? That is the question that reframes finality into continuation, the cosmos not as a closed book, but as a manuscript under constant revision. It is a useful thought because it forces a different posture toward both history and future, one that privileges processes over punctuations. In that spirit, the next chapter of the cosmic manuscript is being written now. The Milky Way is not a static backdrop waiting for an apocalypse. It is on a slow, inexorable collision course with its nearest grand neighbor, Andromeda. The approach is measured in millions of years and in subtle accelerations of gravity, and the encounter will not be a single, cinematic catastrophe, but a protracted, transformative dialogue between two islands of stars. Andromeda is presently roughly 2.5 million light-years away, closing that gulf at a speed on the order of 100 kilometers per second. In cosmic terms, this is a gentle convergence. In human terms, it is immutable and far beyond any immediate apprehension. Gravity, patient and indifferent, binds the local group and ensures that, despite the universe's overall accelerated expansion, these massive structures will meet. The timetable is long by human standards, but short by stellar and geological ones. In about 4 billion years, the first closed passages will occur. Over the subsequent billions, tidal forces will stretch disks into filaments. Gas will be compressed into exuberant waves of star formation. Central black holes will draw nearer and eventually merge, and a new galactic object, some call it Milky Way, will arise from the braided remnants. The mechanics of such encounters are precise yet counterintuitive. When two spiral galaxies approach, their stars rarely collide directly. Space is mostly empty, and the odds of stellar face-offs are minuscule. Instead, the dominant actors are gravity and gas. As the galaxies interpenetrate, each exerts tidal forces on the other. Stars in the outskirts are tubbed into long tidal tails that arc into intergalactic space. Interstellar gas clouds, far more susceptible to collision, crash together, compress, and ignite into new generations of stars. The spectacle is thus a mixture of creation and erosion. Fountains of starburst activity bloom where gas converges, while the well-ordered spiral arms are shredded and reconstituted into a more chaotic morphology. Over several close passes, energy is redistributed, angular momentum is exchanged, and a final, more relaxed, elliptical-like system forms. That transformation is not an annihilation so much as a reweaving. The old order gives rise to new patterns. Giant stars are born at an accelerated rate during the bursts. Their short lives end in supernovae that inject fresh heavy elements into the tumult, altering the chemical landscape for any nascent planetary systems. Central black holes, Sagittarius, and the Milky Way and the large engine at the heart of Andromeda are likely to approach and eventually merge. Their union will generate gravitational waves of enormous power and may trigger luminous quasar episodes as copious gas feeds the coalescing giants. These episodes will be energetic and dramatic on galactic scales, but they are not necessarily apocalyptic for every world. They are catalysts for larger-scale rearrangement. For a small planet bound to a medium-sized star, the consequences are ambiguous. The solar system, like most orbital neighborhoods, is resilient in certain ways and fragile in others. Calculations indicate that direct hits between stars are extremely unlikely. The local densities are far too low for frequent physical collisions, yet the gravitational perturbations of a passing galactic mass distribution can nudge Oort clouds, scatter comets inward, and modestly alter stellar orbits. The result is an elevated cometary flux, an increased rate of impacts that can both deliver volatiles and extinguish surface memories. These showers are themselves slow disasters in the grand sense, the kind of repeated stochastic disturbances that can erase shallow archives and reset the geological clock. Timing complicates the picture further. The close passages with Andromeda will begin near 4 billion years hence. The Sun itself has a clock that will become harsh in a comparable window. Stellar evolution predicts that solar luminosity will increase gradually, warming the planet and straining surface habitability over the next billion years. Several billion years after that, the Sun will swell into a red giant in a cadence that will change interplanetary architecture dramatically. Therefore, by the time the Milky Way and Andromeda complete their merger, any biosphere tied to an Earth-like world will be contending with both stellar metamorphosis and galactic turmoil. The apparent drama of collision is therefore enmeshed with the quieter, unavoidable thermodynamics of stellar aging. Change comes from both without and within. That entanglement between local and cosmic timescales is part of the story's philosophical weight. Deep time reframes ordinary narratives of endings. A planetary civilization that sought to inscribe its presence indefinitely would confront both geological recycling and astrophysical rearrangements. The collision with Andromeda is a salutary example. Even if a species could prepare for a galactic encounter, move to safer orbits, engineer shields, bury archives in stable cratons, it would still be negotiating a multi-layered gauntlet of entropy. Preservation is thus not a single act, but a strategy across scales, balancing the geological with the cosmic. Speculation about strategies is not mere fantasy. Thoughtful projection can suggest robust approaches to long-term memory. The most durable archives will be those that exploit geologic stability and relative dynamical security. Deeply buried isotopic markers locked in cratonic roots have a higher chance of persisting than surface monuments exposed to erosion, tectonics, and impact gardening. Lunar far side deposits offer a quieter surface environment because the Moon is geologically inert compared to Earth and lacks significant atmosphere. A record placed there stands a better chance of remaining legible for billions of years. Trojan asteroids and stable Lagrange points or distant Kuiper belt objects are also candidates. Cold, isolated bodies where implantation of durable data carriers faces fewer erosive processes. The galaxy's collision complicates these options. Distant gravitational perturbations can alter orbital stability over long times, but some niches remain comparatively protected. On an astrophysical level, the collision will be a generator of new chemistry and structure. Starbursts triggered by gas compression will forge fresh heavy elements that will be distributed through supernova winds. In a universe that often seems to be winding down, where star formation declines as reservoirs of cool gas are used up, galactic mergers are episodes of renewed exuberance. They are centers of creation, producing an amplified cadence of stellar bursts over tens or hundreds of millions of years. The merger is, paradoxically, a regenerative act. Where the cosmos is otherwise thinning, collisions concentrate material and produce a flurry of new potentialities. That perspective pushes against fatalism. The universe's long arc includes eras of birth as well as decline. The Milky Way Andromeda encounter will compress time into episodes of intense activity that briefly change the balance between creation and entropy. Yet even in the longer future, when star formation peters out and stellar remnants dominate, there remain modes of evolution, black hole mergers, slow gravitational encounters, and the long chemistry of cooled matter. The universe is not a clock whose hands cease. It is a mechanism that repurposes its constituents, finding new ways to rearrange matter and energy even as overall thermodynamic gradients steepen. For a species that looks forward rather than back, such an eventuality reframes priorities. If civilizations aim to be remembered, their task is to place durable signals where planetary geologic memory and galactic dynamics least erode them. That could mean embedding information deep inside stable mineral matrices, encoding matter itself with patterns that resist chemical transformation, or distributing backups across multiple celestial niches. It could also mean migrating beyond planetary payoffs, sending self-replicating probes to distant halo regions, seeding information across many small objects so that the loss of any one repository does not mean the loss of the archive. These are not guarantees, they are probabilistic hedges, strategies that exchange scale for redundancy and prominence for cost. There are also metaphysical notes embedded in the collision story, less about engineering and more about perspective. two galaxies meeting is a slow reminder that the cosmos is alive with transformation at scales that dwarf human certainties. Empire, civilizational, geological, or biological are brief gestures within that broader script. That realization can either create despair or engender a different kind of pride. An appreciation for the rare window in which a species can perceive scale, ask questions, and choose to act. The knowledge that the universe continues to write beyond any singular demise enlarges responsibility rather than diminishes it. If memory is hard to secure and time is patient in its erasure, then the act of careful preservation becomes a form of moral work, a testimony that even transience can be honored. The collision's scientific promise is also practical. As the two galaxies mingle, they will produce events that afford unique observational opportunities. Gravitational waves from black hole mergers, rapidly evolving quasars, and chemically fresh environments where the physics of star formation and feedback can be studied in situ. For future astronomers, organisms, or machines, that epoch will be a laboratory for understanding how structure forms under extreme conditions. The cosmic narrative is therefore both spectacle and pedagogy, a field where physical law expresses itself in new modes and where questions about the formation of heavy elements, the dynamics of gas, and the behavior of gravity under complex conditions will have rich empirical answers. The final note must be a human one, but it need not be parochial. The continuing convergence of Milky Way and Andromeda is a striking metaphor for renewal. It implies that endings are often just transformations, the rearrangement of ingredients into new configurations. For any civilization that wonders whether to build for the ages, the practical counsel is pragmatic. Preserve where permanence is most plausible. Deep mantle, cold outer space niches, lunar basins, replicate knowledge across media, and accept that some losses are inevitable. Simultaneously, cultivate the capacity to read faint traces, to listen for isotopic murmurs, to decode mineral anomalies, to interpret motions of stars and distributions of elements. The universe leaves multiple kinds of records, some coarse and durable, some subtle and ephemeral. A wise archivist treats both. Ultimately, the approach of Andromeda is not a terminal flourish, but an invitation to humility and curiosity. The cosmos continues to compose, knitting galaxies into new shapes, forging elements in fresh crucibles, and setting long arcs along which matter will be rearranged and memory tested. The Milky Way's future rendezvous is a chapter among many in a history without an author. It does not cancel the past, it repaints it, mixes colors, and offers new canvases. For observers who have the capacity to look up, to measure, and to plan, the collision provides both a warning about fragility and an affirmation of continuity, that the universe does not end in a single event, but keeps opening rooms onto rooms, each offering new margins for wonder, new challenges for preservation, and new reasons to keep writing the story in forms that might outlast a single species, a single epoch, or even a single galaxy.